for the report of the chair membership of the section. This section, our keynote speaker is Professor Dr. Islam Shaya. I will give a brief information about his biography. He is head of engineering and mathematics at Edinburgh University School of Computing, Engineering and Technology Environment. He is a professor of manufacturing engineering. Professor Shaya has worked in higher education for over 23 years. He received his postgraduate certificate in higher education practice from Northern University, a PhD from the University of Birmingham, master and bachelor from Alexandria University. He also worked at Northern University, the Birmingham University, and Alexandria University. He has extensive experience in the conventional and non-conventional machining of composite materials. His work is supported by the UK Research Council, Innovative UK and Industry. Professor Shaya is a fellow of the Higher Education Academy, teaches mechanical and manufacturing engineering courses, and supervises master and PhD projects in advanced manufacturing. He also had honorary post of Newcastle University in the United Kingdom and the Vietnam Journal University in Ho Chi Minh City. He has over 130 publications in journals and international conferences. He also contributes to the global research communities and actively participates as a reviewer for a number of manufacturing and materials journals. Now, I invite you. Yes. His speech title is Innovations in Nanofiber Production, Pioneering Research and Applications.
Okay, good morning, everyone. So, first of all, thank you very much, Chair. Thank you, Professor Hussain, for me correctly. And I would like, first of all, to thank everyone, including the organizing committee, for this excellent symposium. Of course, Professor Ali Demir, Professor Yusuf Ochai, as well as my very good friend, Dr. Ali Klitsch, who is not with us today. So I will miss him so much. So I know we have started late, so I will be quick as much as I can. Okay. So thanks for this beautiful introduction. Today I'm going to talk about a very short title compared to the comprehensive keynote speeches you have heard yesterday. Yesterday, I've heard fantastic keynote talks actually by colleagues, actually a lot. But my keynote talk today is only 2 words: nanofibers and repair. So I have to cover both of them. Okay. So let me start straight away without any further delays. So nanofiber and repair. So remember these 2 words very well. So I'll start actually with repair first, where I'm coming from. Very briefly. I'm coming from a city called Edinburgh, and Edinburgh is the capital of Scotland, which is somewhere in the north of the United Kingdom here. Edinburgh is the capital of one of the 4 nations in the United Kingdom, Scotland. We have fantastic international airports, but more importantly, we have 4 universities in Edinburgh. Because everyone, when I say I come from Edinburgh Repair, they said, "Oh, you come from Edinburgh Welcome." I said, no, Edinburgh Repair, which is a different university than Edinburgh. We have Edinburgh University, Edinburgh Repair, Edinburgh, as well as Queen Margaret University, and we work closely with all of them. And this is a beautiful photo which I've taken myself. I like photographing, so this is where I'm coming from. Okay, in the heart of this beautiful city, historical city, in the center of it, there is a big campus here called Edinburgh Repair University. And the word repair itself is the name of a person. This is a person, actually, called Sir John Repair. John Repair lived 500 years ago. Okay, and he was a great mathematician. He invented decimal points, he invented the logarithms, or developed it because Arabs claim that they have invented it. So there was a bit argument here. But the university has named after this very famous Scottish science, John Polimer. And if you come to visit us, you're more than welcome. I will show one of his homes that he used to live 500 years ago. Still exactly the same furniture, the same ceiling, the same painting. So I'll show you something historical when you come to visit us. Okay, so our university, our top rank was last year. We were ranked top 500 in the Times Higher Education. Now it's slightly below. We have 40% of our students international students, but we have campuses in China, in Singapore, in Malaysia, in many other countries. But the good news, which is not written here, I'm leading another campus, which is international branch campus in Egypt. So our university is opening another campus in Egypt. We are aiming to have 25,000 students in this campus within the next 10 years. So it's a massive, massive development of our higher education in the region. Because our university in the last 20 years, they focused a lot on the Far East of the world. But why I said, where is the Middle East? Where is this area of investment? Very quick about myself. I graduated from Alexandria University, worked and studied in Birmingham. I moved back to Alexandria and moved back to Birmingham. I have a bit of industrial experience, not too long, to be honest. So my higher education career is 24 years now. Only 2 years of them working at Rolls-Royce, trying to develop their engines. So I've done a lot of work on titanium materials. And you'll probably see, actually, I'm a professor of manufacturing engineering. As the chair said, actually, I work a lot in conventional and non-conventional machining. I'm telling you, I work at Rolls-Royce in material like titanium and steel. Why I'm coming here then? Maybe some of you will say, this is the symposium for fiber and polymers. Why are you coming here? You will know that later, actually, why I'm coming today. And I'll tell you a good story about innovation as well. Then I worked as a lecturer at Northumbria University, promoted to become associate professor. Again, this is part of the story, to be honest. Then 4 years back, I moved to Edinburgh University, another beautiful city in the United Kingdom for the last 4 years. I've got over 40 presentations at conferences, 15 keynotes, and a lot of things. In this conference, for example, I was a keynote speaker in Thailand a few years back. I think that was before COVID, and I was talking about machining with composites. Then this one in Japan, I was talking machining with composites again, not polymers, not fibers. And something happened actually, and I started to become involved with ULPAS from 2020, exactly 1 month before COVID. The first ULPAS I had experience with was in January 2020, and after that everything was stopped. Again, this is part of the story that you will know later. Okay, in terms of international recognition for teaching, do a lot in Vietnam, in Mexico, in China. In China again, and we teach because we have lots of programs in China. So I'm trying to be as quick as possible, sorry for the time. In terms of research, I've got 3 book chapters, I've got 2 books actually under my name, and patents as well. But everything related to cutting, machining, metals, where is polymers, where is fibers, and coming. Okay, and these are the 2 books actually I have. Again, citations. As you can see, most of the journals I publish actually, apart from the polymers and metals, the rest are still within the manufacturing area. Okay. So that's quickly about myself, some media coverage as well in the news. This was in a government website. I've got a project here developing one of the industrial pipeline companies in the northeast of England. So my project ranked the first in the whole projects in the United Kingdom. So we are in the news. Again, lots of other news in the media in the United Kingdom. Lots and lots of articles, but I think the most important is here and here. That's why I said Dr. Ali H is actually worked together a lot for the last 6 years. I'm coming from a big team. Our team, engineering and mathematics, is about 50 academics, but only one group working in materials and manufacturing. But the majority of people actually work in materials. Ceramics, electric, not me actually. I work in this composite. Other people work in sustainable material, thermoplastic material, material characterization, and so on. But we also have some people working in manufacturing. CNC machine is myself, spinning is myself, but polymer processing is other colleagues working in the same area. So this is very, very briefly what the first N is. Because as I told you, my presentation is nanofibers, and we have two N's today, N and N. So this was covering the repair part. Nanofiber, which is the second N in my two. Why nanofiber? We're going deeper into the projects and the things I'm going to talk about. Why nanofiber? Very, very quickly, actually. Nanofiber has seen significant demand, or increase in the demand, and there was a report published by one of the very famous publishers. They are predicting the use of nanofibers from 2023 to be 6 times in 2031. It was only 7 years from now, and going from $1.2 billion to over $7 billion manufacturing of the market for nanofiber by itself. So that shows you why people are moving towards nanofiber. So including myself, one of the people have used, working in metals and in composite, the traditional composite for 18 years, and then started to move to nanofiber. Although it happened accidentally, but there is a story behind it. And they also said, oh, most of the nanofibers manufacturing in the last decades happening in North America. That doesn't mean there are lots of other nanofibers in other countries, but the majority of the market in North America. And the typical classification of nanofibers, they can be classified according to their usage, which is the application, like the majority are going to packaging, but some are going to car industry, automotive, and other industries like health and healthcare, and some are very small sector going to coatings. But the other classification, which is a very typical classification of a nanofiber, is according to the material itself. So carbon nanofiber or carbon glass, and the synthetic one, which is polymer, and this is the area I'm now working at. But there are also natural nanofibers, fibers generally speaking, which is a lot of people, especially in the textile sector, are working at. So that's very, very quick overview of the nanofiber. Manufacturing, how people make nanofiber. I think you all know probably better than me actually. The first three, and they are not ranked by any criteria. They're only ranked because I and my team are working in the first three. That's the only reason actually for it. So it's not talking about the size or anything or the importance, but and that shows you actually this diagram published in one of the review papers recently. The number of electro spinning or electro spinning, which is one of the hybrid processing, the increase of the number of research and publications of the spinning activities. Again, lots of applications of nanofibers in the health sector, in filtration, air filtration oil, water separation as well. Lots of applications of nanofibers, as you can see, clearly the majority of the nanofibers applications towards the energy sector as well. Air filtration, this is one of our review papers as well, talking about the use of nanofibers for air filtration, so I encourage you to have a look at that, and lots of other applications in different sectors. So now, I think I covered the two ends. I covered where I'm coming from, the air. I covered also very briefly nanofiber. And it's time to tell you the story behind nanofiber for me. As a manufacturing engineer, graduated with a degree in metals and manufacturing, very traditional machining. I'll tell you the story now. In 2018, I got a call from a friend of mine from Alexandria University, is now Professor Ahmed Hassanein, saying, Dr. Islam, I was a doctor at that time, I was senior lecturer at Alexandria University. I know you work in machining, nothing to do with nanofiber. I said, what's nanofiber? Nothing. I'm very honest with you, nothing happened at that time. He said, oh, don't worry, we covered nanofiber because he studied textile engineering. He was associate professor of textile engineering at that time. But we have another friend, he's a physicist actually, from faculty of engineering as well. So he said, we make nanofiber using that technique called the solution blue spinning. I said, oh, fantastic. He said, I spent some time in Istanbul Technical University, and let's make it. So I said, why me actually? He said, because you are a manufacturing engineer. We need to optimize the process. We need to develop more setups. We need to use your facility scanning electron microscope, which is used between both metals and polymers. I didn't put a lot of hope. And then we applied for a very big grant called the Institutional Research Grant 300,000 British pounds. That's a lot of money, honestly. Okay, that's about like 50 million British lira now, roughly. I didn't put any hope, to be honest, and we were surprised that 2019 they said, we give you the money. Then I'm in the real trouble, how to spend the money. I got like 200,000 myself and 100,000 to Alexandria University. Then I started to work and understand and make partnerships with others, again, like America and other universities actually, and started to build my own team about making nanofiber. And the first part was to recruit people, as I will show you later. But it ended up now, we have grants over £1 million actually of nanofiber work. I'll tell you the rest of this story later. So that's what I'm talking about today. Different nanofiber projects at Edinburgh University in the last 4 years. So the first one is this one, and this is Professor Ahmed Salim. This is Professor Nader Shahada. He works in Greek College of Science and Technology. He works as a professor at Alexandria University. So the first project was to produce ultra-high elastic piezoelectric nanofibers. And then started to look at materials like PVDF, how we look at PVDF, how to optimize the processing, changing the working parameters, making things differently. And the first part was to get one of the Arika's machines, which was a fantastic move, to be honest, because the other option was to do our own setup, which would be very, very time-consuming and the experience. But fortunately, we started to collaborate with Dr. Ali Klitsch at Istanbul Technical University 2019. We purchased one of their machines. And he has finally allowed us to do some work on the machine as well and allowed to increase the productivity, because it was a single dose, mainly lab scale. And that's where I come from in my team. Designing actually multiple nozzle systems, for example, making any improvement to suit our purpose. That's the main thing. It doesn't mean the machine is not good, the machine is fantastic, but it's only to suit our work, who's working on PVDF for energy harvesting application. That is the school behind the school. Then I recruited Dr. Ahmed Rashid, who is one of the research fellows, and Dr. Bawi, another research fellow working in the same project. Again, lots and lots of experimentation, lots of testing in terms of fiber morphology, scanning electron microscopy, FTIR, and many other parameters to assess our improvements. And we have done some, again, modeling, a lot of modeling, again, to control the processing parameters and to ensure that we are reducing the high yield we would like to have. And something like polymer concentration, changing actually, I put some program like TPU in our students. In the other side, the international dimension, that's not in my lab, to be honest, this is in another institution at Alexandria University. We built an old setup for piezoelectric measurement, which is the main criteria of this project actually. Piezoelectric performance of all materials we are fabricating in the United Kingdom. We send it to them and they do all of these electric measurements. We do all of the morphology analysis and they are doing these electric setups using their techniques. So again, applications like two-step simulation, pulsar voltage, and other applications. Things haven't stopped at that time, so this was nearly 2020 once we had COVID, unfortunately. And during COVID, I was about to finish the first project with Alexandria University. And there was another call came. The call is called Newton Fund Impact Scheme. And that's very, very tricky point, by the way, impact. What does impact mean here? They wanted, the British Council, which is the funder of all of these projects, they wanted a team that has already worked together and to receive the previous grants from them, to get them extra money, to develop the technology they are creating, developing, and so on, developing materials or setups, and having a different impact. And you probably remember what happened in 2020. There was a COVID. And we said, why not to start using our PVDF membranes for something like face masks? Will that affect the bacteria growth, for example? Will that have any influence on the virus? And we wrote a grant, we wrote a proposal, very, very good proposal at that time, to claim that using the piezoelectric property and the energy that we can create, we can actually reinforce the filters and we can make something more usable for the health sector. And we got the other grant actually for this, which is nearly £200,000. started in 2022 until end of 2023. So that was a different nature of the project we have, because our application was completely different. We had lots of challenges, to be honest, how we can physically simulate the breathing. Because if we're going to use our material for face mask, how the mask will be charged? We're not connecting a battery. We can't do that for human being. But we were depending on the breathing, like vibration. Will that make any difference? Yes, it did. And we have designed and manufactured a very good setup here. So we can see the setup. It's simulating exactly the frequency of breathing. Probably this is much higher pressure, but that was the initial trial actually. We designed and fabricated something to simulate the natural breathing of human beings, the same frequency. And measured all of the piezoelectric before and after. Not only that, they have done lots of filtration tests. Okay, and again with some help from Dr. Ali here in Istanbul Technical University. And followed by that is done a lot of the antibacterial behavior after this. So the project actually took a completely different direction compared to the first project. Our target was to reduce the bacteria growth. That was the main issue here. And we had another team at a different university, and they have done lots and lots of antibacterial testing. So they took our samples, all of the membranes we have fabricated from PVDF and other materials, they live bacteria, and they left it in the right environment, like medium, far, in the right line, and we have seen significant changes in the bacteria growth within all that we have used our own membrane. So that was actually the second project which ended last year. That didn't stop. When the university sees that I'm bringing more money, they give me more money. So money brings money. So they said, you can have another PhD scholarship, which costs us 100,000 British pounds. But we have to get another application. So I recruited this excellent PhD student, Iman. Iman is working to develop 100% biodegradable, bio-based filters. So that was the target of Iman. So we took it from PVDF, TPU, to completely different biodegradable material. And Dr. Muhammad Reza yesterday spoke briefly about the difference between bio-based, biodegradable, which was excellent. That helped to cut one slide from himself. So Iman also developed the system, and instead of having only a solution flow system, we developed our own electro-spinning system by employing high voltage to the nozzle, as well as developing the hybrid system, electro-blowing system, using our technology at that time. And part of this work was done by one of our MSc students to complete the three systems we developed. Again, lab scale systems for the solution flow spinning, our own electro-spinning, and our new hybrid system, electro-blowing spinning. So the MSc student did a lot of trials again to test this, and we found fantastic outcomes in terms of voltage for the electro-blowing spinning. Then Iman's work herself is based on the rubber material, which is PLA as a biodegradable, as well as bio-based material. So it does have the two advantages here. But we wanted something else. The biomaterial PLA cannot be dissolved in something like other solvent that's not clean. So we then wanted to have 100% clean material. So what we have done is we used actually TMC as a solvent for this setups, and we to ensure that we have 100% filters biodegradable bio-based as well. Okay, so and part of this work we were to investigate the annealing and the effect of annealing of the performance of the biodegradable filtrations of air filtration process we have developed. And as you can see, the best result came for almost all assessment criteria we used for the high annealing temperature, 140 degrees for the face masks. Again, we followed the standard protocol of all testing, including XRD, SEM, IR, and much more assessment criteria. We have also developed our own air filtration setup, so that's all designed and fabricated in our lab, tailored for our lab. So we use the wood, actually, pieces to generate the smoke, use the smoke pump to control the concentration of the smoke. So we controlled everything. We used a couple of chambers here and the particular measurement gauges in both sides, and we put our filters here back in the middle, and we've done a lot of air filtration tests in-house. And we have achieved fantastic results. We managed to control both the filtration efficiency as well as the pressure drop, which is always a nightmare for any filtration actually setups. It's a trade-off between the air filtration and the pressure drop, and we managed actually using our technology to keep that balance between both of them. And all of these are our photos from SAM, shows you how our new masks or filters can very efficiently capture the particulate. So you can see actually how they are being captured within the nanofibers we have today. We developed a couple of piezoelectric setups. One is a standard one, which is impulse loading, so dropping the load. And the other one, which is much more accurate, is using 20 kilohertz shaker, so the shaker can control efficiently the number of pulses that we can measure when the piezoelectric. Things haven't stopped again. So as I told you, I was going to stop working with nanofiber at some point, and then another quote came from the British Embassy in Kuwait, called Kuwait College for Science and Technology. They said, "We've seen your work. Let's give you some money to do something else." And I can say no to the money. So they said, we wanted to have the next green buildings. So the green building now is traditionally made completely out of solar panels. Everywhere is solar panels. Okay. So they said there are some problems. Sometimes when the soil is not probably powered enough energy, starting up this whole system is like that. It's not easy. Can we have an alternative or even a small amount of energy? And then I started brainstorming this idea with my friends. Let's use our material for something to support the green building, the existing green building here. And we thought about developing something called piezoelectric mats using piezoelectric towers of nanofibers, which is very little work has been done. So it's a massive productivity of piezoelectric material stacked together to build actually a maximum energy harvesting from piezoelectric, from food steps. Not only that, we also aim, but this is an ongoing project just started last year, we also aim to get some energy from the acoustic. So even when we talk now, someone with a very loud voice like myself, when we talk actually, if you have curtains fully equipped with piezoelectric material, we can still harvest the energy coming from them. And I have another PhD project working now in this area. So we had, again, a research fellow recruited for that same person, is the Barry, and then we have another PhD student, another excellent PhD students, thanks to Dr. Ian, whose students under the supervision. Maureen Jalali just started like 4 months ago to work on this area. So this is a schematic diagram of the school or the green building, but I wanted to show you the actual green building, which was one of the photos. Oh, sorry. Photos of the time. Okay, sorry. It's probably one of the slides I had to hide because of the time. So this project actually started, and we've done a lot of initial steps. This project was in partnership with an Australian company called Alpha Solar Tech. So they have provided the whole green building. So we have installed the green building itself in Kuwait, and it's again another part of the international work we have done. So we, as Edinburgh University, our responsibility is making the massive and the giant piezoelectric tower that we can make to be installed in the solar or green building here, and that will be coming from Maureen's work as a PhD work. So lots of aims. I'm not going to waste a lot of time. You probably all know why is that. It's of course the carbon emission as well as having the clean energy is very important. This is the progress of the actual work. We used in the initial part some ceramics actually to support the idea of the whole steps, and this system was built in Kuwait. And that's one of the nice photos This is our aim actually, to have the full stack matte completely. First layer is solar, the second massive layer is piezo. So it's a hybrid matte or hybrid floating coming from the combined work between solar as well as the visual. So that's our actually, that's actual physical setup of the green building. It's really big actually, it's more than one bedroom and it has air conditioned, coffee machine, everything is controlled with green energy. Now it's solar, but within a couple of years' time from now, we aim to be hybrid solar and using electric. But last part, which is we haven't even started now, is we have a good idea how to control, how to secure our energy. Will that be our cybercrime in the future? I know we're looking ahead a lot now. Because if we multiply this work in the whole region of the whole country, you might have a cyber attack to control all of the energy. And we wanted to be the first people working on this area. So that was another part. We have professors working on cybersecurity contributing to us and contributing to control the energy. We've got lots of publications. This is only some samples of the publication we got over the last 5 years from nanofiber work at the university. So thank you so much. I'm going to finish again, very different from others. So you've seen what I have done and my team have done actually in the last 5 years. So almost everyone saying thank you for listening. Any questions? But I will do the other way around. Thank you very much for listening. Where would be the next step? What do you think as people working a lot in fibers and polymers? But I have to say, again, thank you so much for your listening, and I'm ready also for the question. Thank you.
Thank you for your nice presentation, Professor Shaya. Do you have any questions to Professor? Yes.
Presentation. I would like a question about fiber annealing. In terms of morphology, after annealing, did you see any differences in terms of length or diameter of the fibers? And my second question is, after annealing again, what kind of properties are enhanced? For example, thermal stability, like that. Thank you very much.
Thank you very much. It's part of the PhD project, as I said. And we have seen after the annealing more, we didn't see any morphological change, massive morphological change in terms of fiber diameters, but we have seen actually a change in the mechanical properties, in particular tensile strength of all of the membranes. So that's significantly affected because we understand what the annealing is doing to any material. Actually, it does improve the crystallinity of the material and the so mechanical tensile strength in particular actually improved, but no changes in the morphology.
Yes.
Professor Islam, first of all, thank you very much for coming here and sharing your experience with us in this 15th ULPAS. And we hope to see you in further ULPAS symposium as well. I very much appreciate your presentation, and I see that we have got lots of projects around nanofibers, and I really congratulate all these. I am only wondering, how are you going to combine the solar panels with the piezoelectric nanofibers? You are talking about some kind of hybridization, but in my mind, I fail to understand. Can you comment on that more?
Yes. That's very, very good comment and the question that I was expecting. But I'll be honest with you, we haven't got an answer yet. Because the project had started with the initial phase, which is making the piezoelectric towers. We haven't even started the linkage between the solar, because this is one of the very, very challenge points of this project, is to put both of them in the same grid of the energy for the green building. Because the green building now, as it's set up, is completely dependent on the solar. And putting another source of energy actually is not that easy. And that's why actually this is a project that we're going to look at this later on.
Okay, thank you.
Maybe next service I will have an answer.
Okay, hopefully.
Our next speaker is Tasim Salame. His speech title is Production of PVP-based wound dressing loaded in autoclave. Yes, you can come. He is a mechanical engineer with experience in CAE5, especially in injection molding. He worked with other engineers from different backgrounds and different nations, including collaboration with engineers from Novares Group. I think you are a master's student now in Istanbul Technical University. Yes, you have 20 minutes.
Thank you for the introduction. Good morning, everybody. Thank you for coming. I'll be discussing my project concerning the production of PVP-based wound dressing loaded with article wound. I'm going to talk about generally about wound dressing in general. The production method we used, and then we're going to take a look at the results, mainly concerning the nanostructure and the drug release of the dressing. So to start with, the main idea of the project is to produce wound dressing loaded with a certain drug. And upon application directly to the wound, the drug will be released gradually over a period of time. And depending on the type of wound, a certain drug can be selected, which will be suitable for aiding the healing process of the wound. Concerning wound dressings in general, they would depend on, especially if we're talking about modern wound dressing, they would depend on the type of wound. Now, there are two types of wounds, acute wounds and chronic wounds. Acute wounds are those that go through the normal process of wound healing, inflammation, tissue proliferation, and then remodeling. On the other hand, chronic wounds are those that fail to undergo this natural process, or let's say normal process, and because of infection, the inflammation phase of chronic wounds extend for a longer period of time. And this extended inflammatory phase is what causes the creation of chronic wounds. Traditionally, wound dressings were mainly in the shape of gauze, so they were mainly concerned with covering the wound, insulating it from the environment. But modern wound dressings are more concerned with aiding the healing process. And one of the modern wound dressing solutions is to use hydrogels. Hydrogels are hydrophilic materials made from synthetic fibers. They possess high water absorbability, and they aim to preserve a moist environment around the wound. To make advantage of wound dressings, especially hydrogels, a certain drug can be loaded into the polymer that creates these hydrogels. And you can see here a sketch that shows you the fibers making the hydrogel and the molecular structure, which will be polymer and loaded with the certain drug. Using solution blowing will allow for advanced fluid exchange between the wound dressing and the wound itself, since the mass created by solution blowing would have high porosity and would allow for water and air variability. About solution blowing, Mainly, solution blowing consists of pumping a certain solution, which will be consisting of solvent and the material in question. In our case, it was the polymer PVP and the drug atuvacune. And around this pipe, compressed air will be provided. This configuration will make the droplets of the solution extended, deformed to take a nanofiber structure. The thickness of the resulting mat will depend on the time of production. So production can continue for a longer period of time without sacrificing the morphology of this nanostructure, nanofiber structure. After solution blowing, branches of the mat were taken and put in oven for cross-linking. We did not use a cross-linking agent since we didn't want to add any contamination to the wound dressing. So only thermal cross-linking was used. PVP has a glass transition temperature of 160, around 161. So we did the thermal cross-linking at 160. As you know, in cross-linking, the polymeric chains are linked to each other. Forming a network. This network would prevent individual chains from slipping into liquid motion, and thereby maintaining the overall geometry of the wound dress. To test for the success of this thermal cross-linking method, we used swelling experimentation. So the idea being, if the cross-linking was not enough, was not sufficient, the mat will break apart and dissolve in water. The uncross-linked mats will dissolve immediately, actually, in water. So we took 3 groups and put them in oven for 1 hour, 2 hours, 4 hours, and then put them on water to see their behavior. The group that was thermally treated for 1 hour actually broke immediately and dissolved in water, so that wasn't sufficient. However, both 2 hour and 4 hours group showed similar results. They both maintained their shape, they remained intact, and also absorbed similar amounts of water. You can see the 2 columns on the right for the groups for 2 hour and 4 hour cross-linking. Similar moisture content was added to them. These were drug-free groups, just to see the main idea of cross-linking. Then we added a drug-loaded group, you can see on the left, and the additional drug did not hinder neither the cross-linking nor the moisture absorbability. Moving to the morphology of the fibers, you can see here a picture of the produced raw nanofibers, so without cross-linking. And solution blowing managed to create nanofibers with high uniformity, so there was not a lot of variation in diameter. One factor we find that should not be underestimated is viscosity. As more drug is added to the solution, the more viscous it becomes, and problems start to appear in the solution blowing system. That is like clogging, creating droplets. So there's a certain limit above which we can't continue with the system. But even below that limit, there was an observable effect of viscosity, and that appeared as a change in diameter. The picture on the left shows you the drug-free group, while the picture on the right shows you a group loaded with 10% of the drug stock, and we can see a drop in diameter from 650 to 470 nanometers. And overall, the structure remained quite similar. And moving to the effect of cross-linking. Of course, we cannot apply the new dressing without cross-linking. It will dissolve immediately. So what happens in cross-linking, you see some fibers deformed in shape. They become curved, and some of them joint at certain points. You can see here. These joints, of course, are not cross-linking joints. Cross-linking takes place at a molecular level. But these deformations happen because we are treating at temperature near the glass transition temperature. And when we put the mats in the oven, they experience thermal shrinkage. It's not massive, it's not visible with the naked eye. But you can see that on the nanoscale, thermal shrinkage does have a quite significant effect. Again, adding the drug to see whether the drug itself would affect the cross-linking process, but we see similar results also. Joints here, and some fibers bending. In this picture, you can see clearly the formation of agglomeration. Some agglomeration happened. This is the same polymer, no other material was used, but this is because of the thermal treatment. However, we can also see larger spaces and curvatures in the structure. These would help holding the water droplets, and that would explain the very high water absorbability. Adding the drug to see the effect, you can see similar results. Even after the agglomeration happens, still the structure is quite permeable and easily absorb water and provides energy. To test that exactly, we did a permeability test. There was a small drop before and after cross-linking for each of the test groups, but in the end, the mats remained comfortably providing air breathing for the skin. However, it should be noticed that the mats we produced are quite thin. You can see 70 to 90 microns and so on. So if thicker mats are required, this might be taken into consideration. Finally, of course, the drug release itself. So we made a small experiment to test for the drug release. We took small pieces of the mats and fixed them in place, subjecting only one phase to the PBS buffer solution. And we took samples at several time intervals, analyzed them with HPLC, high performance liquid chromatography, which reviews data, and based on the area under the curve that corresponds to the concentration. In the end, overall, we managed to create a cumulative drug release profile. We can see that by 1 hour, almost 80% of the drug was released, which is quite a fast release. And by 12 hours, almost all the loaded drug, 95%, was released into solution. So we concluded from our project that it was possible to produce these masks with solution level and both chemical drugs, and we did have a successful release of the drug into the buffer solution. However, the release profile might need enhancement to make it slower and for longer periods of time. And we shouldn't forget that there is a limit to how much drug we can load into the mats because of the viscosity limitation. So that was my presentation. be glad to have any of your questions. Thank you.
Thank you for your presentation. Do you have any questions?
Thank you for the presentation. Did you do any work about the effect of the blowing on the diameter of the fibers? Did it reduce the diameter of the fibers?
We found that increasing pressures in the solution flowing process reduce the fibers in general, yes. But if we increase the pressure too much, we would also have droplets. And the resulting fiber will not be coming continuously from the nozzle, but rather it will be coming like splitting. So it's a droplet strain rather than nanofibers.
I have one question. Here, I'm here. What is your temperature for cross-linking? Which temperature is enough? Did you test?
We used 160. That was enough. We didn't want to go for much higher temperatures because we didn't want to degrade the drug. Lower temperatures were also far from the glass transition temperature, so they would not be sufficient for cross-linking.
I think you have a question. Okay.
Awesome. Thank you very much for your presentation here. While you are making this cross-linking, I was wondering what's happening to the drug. Did you check whether it is decomposing or affected?
Testing for using the HPLC technique requires testing the drug itself first. So we make a dilution series first for the drug, so it cannot be subjected to any temperature. And for successful data review after that, there will need to be the same, let's say, fingerprint for the drug. So if any decomposition took place, it will not be detectable anymore. So since we detected it, it should be the same.
Okay, thank you.
Okay, thank you for listening.
Our second presentation is air probability of printed with car mask, including various layers. Gonca Alan. Dr. Gonca Alan is working as a doctoral research assistant at Uşak University, Faculty of Engineering and Natural Sciences, Textile Engineering Department. After completing her doctoral education at Uşak University in 2018, she continued researches on non-woven surfaces, recycling and sustainability concepts in textiles, and usage performance of spatial fabrics, both on the domestic and international platforms. Finally, he spent 1 academic year at the University of West Attica, Greece, to do a postdoctorate. Yes, Dr. Gonca.
Thank you for your kind presentation and introduction. Dear audience, it's a great pleasure for us to be here today, and thank you for your participating to our presentation. My study with my colleagues has to do with air permeability of printed and unprinted masks, medical masks used for pandemic outbreaks. And we try to use various layers in different layers and constructions to detect the effect of layers to the air probability of the masks. Let me give you a very short introduction to our issue. As we know from the pandemic crazy period, medical masks have significant role in abating spread of infectious diseases and potential threats such as pandemic or epidemic outbreaks coming over and over again. So we use them for we use them for 3 or 4 layered forms. And the layers has to do with the closest form of the wearer's skin should be an absorbent material to take the moisture coming from the wearer's breath. And the middle layer should be consisting of like a muffled fabric, just to act like a filter layer. So, and lastly, and most commonly used 3 layers were made up of water-repelling tissue. So we have to choose them with a systematic way. And they are most commonly used for nonwovens in conventional textiles, as conventional production techniques of nonwovens. We use them for their cost effectiveness, for their tailorable ease of use, and because of their time-saving production skills. So one of the most commonly used way of producing nonwovens can be defined as nonwoven, as we know, and it's a conventional manufacturing method of nonwoven surfaces, which is allowing to the raw material polymer melt, extruding through the dozens of tiny nozzles by high-speed blowing gas. As the raw material for this type of production method, in nonwovens, we know polypropylene and polyethylene fibers are most commonly and majorly preferred due to their hydrophobic nature and cost effectiveness, as we know. On the other hand, as secondly most commonly used methods for producing nonwovens, we can be concerned with spinning technology, in which raw materials are extruded onto a conveyor via spinneret in melted form. So, when it comes to the usage areas and application areas of spin-on nonwovens, they are rather preferred for their usage areas such as medical and healthcare, and packaging and protective materials and filtration, also in skincare productions. So another technique to maintain nonwovens which are used in hydrophobic forms or layered masks is spun lacing. And in this technique, we use an entangling web made of loose fibers, which allows to be mounted on the porous belt milling perforator or pattern screen to form a sheet. And these structures, by exposing the fibers multiple rows, have tiny high-pressure jets of water, which is entangled by them all. So, spoon-laced surfaces can be used for surgical bones and wipes and skincare spoon-laced facial medical masks for their good relationship with human care and skincare health instructions. Lastly, I would like to mention about, just with a sentence, with thermobonded nonwoven surfaces and their production method. As we know, they are considering different proportional binder fibers, directions of web length, bonding time and temperature as variables. They are commonly used as the outer layer parts, which is water repelling part of the 3 or 4 layered masks in healthcare instructions. So thermobonded surfaces made of staple fibers have interconnected pores and tortuous pore paths through the fabric thickness. This allows the droplets of the air and water repelling properties enhanced by these techniques. So, we faced with different kinds of studies which are mainly focused on filtration efficiency and effects of manufacturing parameters on performances of the surfaces which are used as layers for the masks. So besides conventional manufacturing techniques, performances of functionalized surfaces and color fitting and fitting perception of medical masks are also studied in this sector. From another aspect, medical masks for children usage is an attractive issue for researchers as well. In the aim of our study, we tried to evaluate the air permeability values of the fibers entanglement in the masks forms of the nonwoven layers from the outer and inner layers of the masks. Secondly, the number of layers were in our concern as well, and the type of the outer layers, such as printed or unprinted, was our another aim to evaluate from the performance parameters of air permeability of these masks. So, the effects of printed layers in the masks on air permeability were ruled out, and also the effect of number of layers and type of the masks from unprinted and printed point of views were analyzed. For this purpose, we used 3 or 4 layer masks to prepare our masks placement and the layers used at this stage. And the properties of the masks are presented in table 1, as you see. We used spoon-bound 3 layers masks and spoon-bound 4 layers masks, and thermobond 3 layers and 4 layers masks again. Then spoon-lace outer layer, 3 layers and 4 layers masks were equated and lined from the sacral isolation in 100 and 110 total grams per square meter were adjusted in our placements. Then, as the procedure itself allowed us to evaluate the air permeability values according to the standards, and the masks were tested on both outer layers and inner layers. So, in the evaluation, outer and inner layers of the masks, number of layers and of layers were taken into consideration, and the obtained results were statistically analyzed through programs. So, when it comes to talk about the results in the discussion part, we try to examine from the point of view outer and inner layers. For 3 layers ones, inner layers air permeability values were higher in spoon-bound masks. On the other hand, outer layer air permeability values were higher in thermobond masks and spoon-lace ones. So we got it in pocket and moved on. For 4 layers, outer layer air permeability values were higher in spoon-bound masks and thermobond masks. Moreover, inner layer air permeability values were higher in spoon-lace ones. The effect of outer and inner layers on air permeability was found to be statistically insignificant on the other hand. From the aspect of number of layers, it was observed that the air permeability values of 4-layer masks were higher than that of 3-layer ones. So the fact that this result was obtained in the masks with a compatible total weight in grams can be attributed to the use of lighter layers in the middle and inner layers of 4-layer ones. In addition, the melt-blown layer is known to have an effect to lower air permeability, and the fact that weight of the melt-blown layer in 3-layer masks is higher than in 4-layer masks support this result as well. So we observed that this effect is statistically significant. When it comes to from moving to printed and unprinted ones, while in the middle and inner layers were the same, the three-layer masks, it was observed that the highest air permeability value was seen in spoon-bound ones in both outer and inner volutes. Spoon-based masks values followed the spoon-bounded ones, and the lowest values were observed in thermobound masks. In four-layer masks, it was determined that the highest air permeability values were seen in spoon-based masks in both outer and inner volutes, followed by spoon-bound masks, and the lowest were again in thermobound ones. So the air permeability values did not have a statistically significant effect as well. To sum up and to have a conclusion, when the values were examined in general, it was determined that the outer and inner layer air permeability values slightly differ, and the difference between them was not statistically significant. So from the aspect of from number of layers, it was determined that in the mask with a compatible rating grams in total, the air permeability values were in 4 layers masks consisting of lowering grammage layers were higher than those of 3-layered ones with higher grammage layers. So in order to compare printed and unprinted medical masks, when the middle and inner layers were kept the same, the air permeability values were compared according to the outer and layer type, and it was seen that the air permeability values according to the outer layer type did not create a statistically significant difference. In other words, it can be said that there is no significant decrease in the air permeability values of printed medical masks prepared especially for children compared to unprinted ones with compatible total weighting grams. So thank you for your attention. If you have any questions, I would be glad to answer if I can.
Yes, do you have any questions? Thank you.
You're welcome.
Presentation. These results are expected results for 3-layer or 4-layer layered mask.
Yes, actually, you're
Because air permeability is depends on the layers.
yes. Fundamentally, actually, we were expecting these results coming as well like this. But as a part of a bigger projection or visualization from our project, this was the first step to analyze if these results were taken for, especially in children masks. So we would like to take a step with making them sew with different temperature sewing and making them together again. So it was the first step of our bigger part of that project here. Thank you for your question.
Thank you. I was really surprised that your 4-layer had higher air permeability than the 3-layer. Could you explain that a little bit more?
With pleasure. Thank you for your kind interest and question. Actually, these 3-layer masks were not surprising because we know that they have an upload layer as the interlayer. So in 4-layer ones, we try to use lighter spoon place and spoon bond tissues to lower the air permeability if we can compare it with 3-layer ones. So yes, we have 4 layers, but we have thinner and lighter 2 different layers inside instead of melt-blown ones. So melt-blown ones are known for providing the lowering effect of air permeability, and we wanted to enhance the second chance with spring-lace ones and spring-on ones in thinner forms, keeping the total in weight grams as 100 and 110 grams per square meter at all.
Thank you again. Our next two presentations will be in Turkish. Now, our presenter is etmektedir. His speech title is Biyopolimer ve biyokompozitlerin mekanik özellikleri üzerine üretim parametrelerinin etkisi. Bundan sonra sanırım biraz Türkçe devam edeceğiz. Buyurun, başlayabilirsiniz.
Teşekkür ederim. Merhabalar. Okulumuzun böylesine bir projeye ev sahipliği yapması beni gururlandırıyor, söylemek istiyorum. Bu okulun parçası olmaktan gurur duyuyorum. Öncelikle bugünkü konumuz biyopolimer ve biyokompozitlerin benim çalışmam konusu. Biyopolimer ve biyokompozitlerin üretim parametrelerindeki değişikliği, bu üretim parametrelerindeki değişiklikteki mekanik özelliklerin değişimine vurgu yapacağım bir konu. Öncelikle girişten bahsedip sonrasında literatür sonuçlar ve iletişim yapacağım. Genel olarak günümüzde en büyük sorunlardan biri çevresel sorunlar. Bu çevresel sorunları önlemek açısından biyopolimerler ve biyokompozitler büyük önem taşımaktadır. Bu yüzden bu çalışmada bu değerlerin optimize edilerek daha fazla biyopolimer ve biyokompozit çeşitlerinin üretilerek her alanda kullanılmasını sağlamak istiyoruz aslında. Buradaki çalışmanın amacı da farklı değerlerdeki ve farklı parametrelerdeki değişimlerle malzemelerin üzerindeki değişimlerin mekanik özelliklerdeki etkilerini incelemek ve buna göre yeni ürünleri elde etmeyi sağlamak, çalışmak. Öncelikle biyopolimerlerden bahsedeyim. Doğal kaynaklardan elde edilen biyolojik olarak parçalanabilen polimerler bunlar. Nişasta, selüloz, proteinler tarafından üretilir ve yenilebilir olması açısından çevresel olarak avantajlı malzemelerdir. Birçok alanda, tarım, tekstil, ambalajlama alanında da birçok alanda kullanıldığını görebiliriz zaten. Biyokompozitlere baktığımızda da yapısında biyobozulabilir maddeler kullanılan en az 2 veya daha fazla maddenin birleşimiyle oluşan malzemelere kompozit adı veriyoruz. Bunların yenilenebilir olması ve doğal kökenli olmasına da biyokompozit adı veriyoruz. Üretim yöntemlerine baktığımızda birçok biyopolimer üretim yöntemi bulunmakta. Bunlara fermentasyon, enzimik polimerleşme, biyosentez, asidoliz, biyolojik yerleşme olarak örnek verilebilir. Yani bunların nasıl üretildiği de mesela fermentasyonun mikroorganizma kullanılması ve kullanıp mayalanmasıyla üretilir. Yani bu şekilde doğal reaksiyonlar neticesinde gerçekleşiyor bu üretim yöntemleri. Bu zaten onu çevresel olarak avantajlı kılmakta. Biyokompozitler de ana yöntemlerden, en çok kullanılanlardan bahsedeyim. Ekstrüzyon, enjeksiyon kalıplama, kondensasyon polimerleşmesi gibi şeylerde kullanılabiliyor, üretim yöntemleri kullanılabiliyor. Ekstra devam ettiğim sayfada da devamı vardır zaten. Termoformlama, solvent döküm gibi yöntemler kullanılmakta. Bizim okulda da en çok çalıştığımız çalışmalardan biri de zaten üstüne baskı eklemeli üretimle gerçekleşiyor. Burada katman eklemeli üretimle en çok kullandığımız ve geliştirmekte olduğumuz projelerde bunun üzerine. Güncel olarak zaten dünya tamamen üstüne baskı yönlenmesine gittiği için biz de bu konuda daha fazla çalışma gerçekleştiriyoruz bölümümüzde. Malzemeler üzerindeki parametrelere değinmiştik. Bu parametreler nelerdir? Üretim sıcaklığı, üretim hızı, ortam koşulları, basınçların değişmesi, katkı oranlarının değişmesi, bu gibi etkenleri değiştirerek malzemenin mekanik özelliklerindeki etkiyi incelemek, bu konuda derleme çalışmalarını yapmak için bir sürü makaleden alıntı alıp bu makalelerdeki değişimi inceleyerek buradaki hangi katkı oranında hangi malzemeler nasıl davranış göstermiş, mekanik özelliklerden neyi etkilemiş, bu şekilde inceleme yapıp kendimize aslında bir el kitabı gibi bir makale oluşturmak istiyorum aslında. Mekanik özellikler nelerdir, nasıl ölçülür, buna değinmek istiyorum. Çekme testinde elastik modülü, uzama, akma mukavemeti ve çekme mukavemetini bulmak için kullanıyoruz. Sertlik bulmayız. Zaten sertlik, short, because, biriner gibi sertlik testleri kullanarak sertliğimizi ölçüyoruz. İlk olarak literatür çalışmalarında üretim yöntemindeki uygulamanın değişimini örneklemek istedim. Birçok makaleye baktığımda hepsini koyamadım çünkü review makaledeki örneklem sayısı çok fazla ve örneklem sayısını arttırarak en iyi sonuca ulaşabiliyoruz. Ama ben sadece her bir üretim yönteminden, katkıdan, hepsinden birer tane örnekler verip kısa tutmak istiyorum. Öncelikle polilaktik asitteki enjekte edilerek, enjekte edilmiş ve ekstrüde edilmiş yöntemle, tavlama yapılmış yöntemle ürünlerin elastik modül değişimi, akma mukavemeti ve uzama değişimleri görebilirsiniz. Buradaki değişimlere sonucuna en sonunda değineceğim. Öncelikle sonuçlarını göstereyim. Bu şekilde malzemelerde katkı enjekte edilme yöntemlerle değişmesi, enjekte edilip tavlanmasıyla malzemenin elastik modülünün arttığını, akma mukavemetinin hepsinin doğrusal oranda arttığını, sadece uzamanın belli bir optimize değerinin olduğunu söyleyebiliriz. En sonunda sonuçlara değindiğimde de zaten buradan bahsedeceğim. Diğer bir kitin oranına göre mekanik özelliklerin değişimi, burada katkı oranına ve malzemenin kesim yönüne, üretim yönüne göre değişimini incelemiştim. Buradaki makalede de, makale ve çalışmada ise malzemenin polihidroksilikatın makine yönüne göre normal üretimi söz konusu. Bunun hem makine yönü hem enlemesine yönde sertlik ve çekme, elastik uzama sonuçlarını görebilirsiniz. Buradaki sonuçlara da yine sonunda sonuçta değineceğim ama farklılıkları gösterecek olursam öncelikle ilk ikisini ayrı değerlendirmek, sonrasında katkı oranlarını ayrı değerlendirmek gerekebilir. %1 kitin nanokristalleri katkılı iki malzeme var. Orada %1 olarak hem makine yönü hem de enine yönünde deneme yapıldı. Sonrasında %5 oranda kitin nanokristali eklenerek hem makine yönünde hem enine yönünde deneme yapıldı. Sonucundaki sertlik oranlarında enine yönde genel olarak daha düşük çıktığını söyleyebilirim. Ek olarak başka bir parametrenin değişimi olan ortam koşulları ve gamma ışığı radyasyonuna maruz bırakan malzemelerin sonuçlarına değineceğim. Burada kefren film kullanılmış. Öncelikle kullanılan kefren filme 3 kilogray, 6 ve 9 kilogray olmak üzere 3 farklı ışına maruz bırakıldı. Sonrasında bunun mekanik özelliklerinden çekme ve uzama mukavemetinde sadece inceleme yapılmıştı. Bu malzemenin sonuçlarına da yine aynı şekilde bir sonraki sayfada değineceğim. Bu sonuçlar neticesinde ilk olarak malzemenin biyopolimer ve biyokompozit uygulamaya göre özelleşmesi gerektiğini gösteriyor. Bu malzemelerin farklılıktaki sebeplerinden biri olan parametre değişimi, tavlama, ekstrüzyon işlemleri tercih edilirken, mesela örnek olarak yapısal dayanıklılık istiyorsak, tavlama ve ekstrüzyon işlemleri tercih edeceğimizi söylüyor buradaki ilk makalemiz. Çünkü değer olarak daha fazla bir değer veriyor bize. Ama aynı şekilde uzamadan sıkıntı çektiğimiz için de esneklik ve şekillendirme kapasiteleri ön planda ise de enjeksiyon ve ekstrüzyon gibi işlemleri tercih edebileceğimizi çıkarım olarak yapabiliyoruz. Yani bu makalenin temel amacı da hangi özelliği istiyorsak ona göre üretim yöntemi ve katkı oranını belirleyebileceğimiz bir kitap elde etmek, el kitabı gibi bir sonuç elde etmek istiyordum. Burada ekstra olarak diğer araştırdığım makalede ise polihidroksilikat'ta çift vidalı ekstrüzyonla üretilmiş olan bu malzeme çift vidalı kullanıldığında kitin nanokristalli oranının artmasıyla makine yönündeki ürünlerin tercih edilmesi, biyokompozit mekanik özellikleri optimize etmek için önemli bir yol olabilir. Çünkü burada şöyle göstereyim. Oran arttıkça, malzemenin oranı arttıkça belli bir artış olmuş. Ama sonrasında makine yönünde enine yönde yapıldığında bir düşüş gerçekleşmiş. Yani bu enine yönü mü, makine yönü mü yapıldığını, testin yapıldığını ve katkı oranının artmasıyla malzemenin sertliğinin arttığı söylenebiliyor. Yani bu kitin nanokristalleri malzemenin sertliğini ve elastisitesini arttırmış diyebiliriz. Ek olarak ketilen polimerlerin maruz kaldığı gama ışını dozajının artması çekme dayanımını 3 katına kadar çıkarmakta. Ama uzama miktarında %57 oranında düşürmekte. Yani bunların ters orantılı bir artışı var. O yüzden bir optimize değer sonucu elde etmemiz gerekiyor. Burada da gördüğünüz üzere zaten ketilen filmler gama ışığı 3 kilograyle düşükken 9 kilograyle yaklaşık 3 katına kadar çıkmış. Yani ana malzemeye göre. Uzama miktarı da aynı oranda %57 oranında düşmekte en baştan sona doğru. Bu sonuç ışığında malzemenin hem çekme mukavemeti yüksek bir malzeme hem de uzama miktarı yüksek bir malzeme olmasını istemeyiz. Bu yüzden bunun optimal değer olan 6 kilogramı daha kabul edilebilir bir malzeme olduğunu söyleyebiliriz. Daha birçok aslında makale içinde birçok sonuca değinmiştim ama bunun hepsini koyup uzatmak istemedim. O yüzden her katkı oranından birer tane, bir parametre içinden birer tane koymak istedim. Buna göre malzemede verilen katkıların mekanik özelliklerde nasıl bir değişim isteniyorsa ona göre katkı oranı yapmamız veya ona göre üretim yöntemi belirlememiz gerektiğini söyleyebilirim. Şimdi gelecek araştırmalarda katkıda bulunacağını tekrar söylemiştim. Mesela bir çalışma yapıyoruz. Bu çalışmanın içinde hangi mekanik özelliği istediğimizi daha önceden belirlemiş oluyoruz aslında. Bu mekanik özelliğe göre hangi üretim yöntemini kullanacaksak ona göre katkı oranını kolayca belirleyip seçebilmek açısından önemli bir yol izleyeceğimizi düşünüyorum. Sürekli yeni malzeme arayışı devam etmekte. O yüzden de yeni malzemeler bu sayede üretilmiş olacaktır. Dinlediğiniz için teşekkür ederim. Heyecanlı kusura bakmayın. İlk sempozumuz.
Referanslar kalsın orada. Öncelikle cesaretine ve sunumunu tebrik ediyorum. Yani güzel bir başlangıç, güzel bir çalışma yapıyorsun. Ancak referansları özellikle tuttum. Referansların neredeyse tamamı İngilizce dilinde yani yabancı kaynaklı. Bir tane sanıyorum. Türkçe var mı? Türkçe yok.
Bir tane olması lazım.
Keşke sen de sunumunu çalışmanı İngilizce olarak İngilizce çok daha hem senin için hem bizim için çok daha faydalı olur.
Ben o yüzden daha çok gerildim aslında. Herkes İngilizce yapıp ben Türkçe yapmaya başlayınca o yüzden orada gerilmeye başladık.
Bir dahaki sefere inşallah İngilizce bekliyoruz. Tebrik ediyorum. Bir de bu güzel bir literatür derlemesi, güzel bir çalışma. Buna paralel küçük bir deneysel çalışma da yapabilsen çok daha güzel şeyler.
Aslında hani deneysel çalışmayı bunun sonucunda değil de review makaleyi yazdıktan sonra buna bir içindeki malzemelerden çıkan sonuca göre bir yol haritasına göre bir yapmayı düşünüyoruz zaten hocamızla da.
Tebrik ediyorum.
Teşekkür ederim.
Section'da son sunumumuz kemik doku mühendisliği uygulamalarında polilaktik asit PLA kullanımı. Rümeysa, değil mi? Evet.
Kendimi tanıtım İzmir Bakırçay Üniversitesi'nde doktora öğrenimi görmekteyim. Yönetilen mühendisliği. 3. dönem yeterlilik bölümündeyiz. Sunumumuza geçecek olursak da kemik doku mühendisliği uygulamalarında polilaktik asit kullanımı hakkında benim de bir derleme, literatür taraması tarzında bir anlatımım olacak. Sunum içeriğimiz kemik doku mühendisliğine neden ihtiyaç duyuyoruz? Kemik iskelesi üretim yöntemleri nelerdir? Kemik doku iskeleleri için eklemeli imalat üzerinden iskele üretimine değineceğim. Biz kemik iskelelerinde özellikle bu çalışma için polilaktik asitle kemik iskelesi üretimine odaklanacağız ve neden PLA'yı seçiyoruz? Kemik doku mühendisliği uygulamalarında PLA'nın kullanımı sonrasında da sonuç ve gelecek perspektifine bakıp bitireceğiz. Kemik doku mühendisliğine neden ihtiyaç duyuyoruz? Kemik dokusu aslında normal şartlarda az miktarda bir hasara uğradığında kendini yenileyip onarabilme yeteneğine sahip olan bir doku olmasına rağmen büyük kusurları onarmakta yetersiz kalmakta ve bu gibi durumlarda klinik müdahale gerekmekte. Büyük ölçekte oluşan kemik defeklerini onarmak için de otogreft, xenogreft, allograft gibi uygulamalar gerçekleştirilse de özel eksikliği, genetik farklılık, enfeksiyon ve doku reddi sebepleriyle sınırlamaları olmakta. Bu sebeple rejeneratiflik ve kemik doku mühendisliği bu kısıtlamaları gidermek için ortaya atılmış bir alan olarak önümüze çıkıyor. Dokuların kaybettikleri fonksiyonları yeniden hazırlamak, yeniden sağlamak üzere hücreleri ve biyomalzemeleri kullanan doku mühendisliğinde osteoblastlar ve yapı iskeleleri esas alınmakta. İdeal olarak vücut içerisinde biyobozunun özellik göstermesini istiyoruz biz bu çalışma kapsamında. Bu sebeple de biyobozunur plastik polimerlere odaklandık. İdeal olarak uygun yapısal ve morfolojik özelliklere sahip doğal veya sentetik biyomalzemelerle biyoürünü ve biyobozunur olarak üretilen iskeleler hücrelerin bağlanmasını, çoğalmasını ve büyümesini kolaylaştıran yapılar haline almakta. Bu görselde de doku iskelesinin, kemik doku iskelesinin 3 temel aslında yapı taşı var diyebiliriz. Hücreler, biyosinyal moleküllerimiz, büyüme faktörlerimiz ve doku iskelemiz. Doku iskelemiz aslında biyouyumlu olduğu müddetçe biyoseramikler, polimerler ve metalik malzemelerden elde edilebilmekte. Ancak burada biyobozunur polimerlere odaklanacağız. Kemik iskelesi üretim yöntemleri olarak geleneksel üretim yöntemlerimiz de var. Çözücü döküm, partikül uzaklaştırma, gaz köpürtme, dondurarak kurutma, elektrospinning ve son zamanlarda 3D baskı hızlı prototiplemenin biyomedikal alanda da sıkça kullanılmasıyla birlikte kemik iskelelerini 3D yazıcılarda da üretilebilir duruma geldiğinde. Ama her birinde üretilen gözenek boyutları ve iskele yapısı farklı olmakta. İskele yapılarının ve gözenek boyutlarının farklı olduğunu söylemiştim. Mikropor, mikrofiber ve nanofiber yapıda olan kemik iskelelerinde hücrelerin iskeleye tutunma tepkileri de farklı oluyor. Burada mikropor, yani mikro gözenekli veya mikro lifli yapılara sahip yapı iskelelerine bağlanan hücreler düz ve yayılan bir şekilde bağlanırken nanolifli yapıya sahip iskelelerde hücreler hücre bağlanmasını daha çok yönlü sağlayabilmekte, hücre etkileşimini artırmakta. Peki kemik iskelesinin aslında ihtiyaç duyulan özellikleri ne olmalı? Bozulma hızı öncelikle önemli olan. Çünkü kemik iskelesine gerçek osteoblast, yani mezenkimal kök hücreleri ekledikten sonra entegre olmasını bekliyoruz gerçek doğal kemik dokusuyla. Ve entegre oldukça biz istiyoruz ki kemik dokusu yavaş yavaş bozulsun ve gerçek kemik yerini alsın. Oluşturulan kemik iskelesi bozulacak ve gerçek kemik iskelesi yerini alacak. Ve bunun da kademeli olarak olması gerekmekte. Mekanik özellikleri de tabii ki gerçek kemik yapısıyla eşdeğer olmalı. Gözenek boyutunun da önemli olduğundan bahsettim. Vaskülizasyonun ve besin aktarımının daha kolay olabilmesi açısından ve biyomalzeme seçimi. Kemik doku iskeleleri için eklemeli imalat. Bu nasıl uygulanıyor? Hastanın kemik defekti olan bölgesinden tıbbi görüntüleme yöntemleriyle 3 boyutlu görüntü elde ediliyor. Bunu daha sonra bilgisayar destekli tasarım görüntüsü elde ediliyor. Daha sonra iskelenin baskısı yapılıyor ve içerisine hücreler, işte sinyal molekülleri, büyüme faktörleri eklenerek ya bir biyoreaktör içerisinde olgunlaşması bekleniyor ya da canlı ortamda büyüyüp gelişmesi bekleniyor. Daha sonra da hastaya implante ediliyor. Tüm bunlar ışığında da kemik iskelesi üretmek amacıyla biyouyumlu ve biyobozulmuş, düşük maliyetli ve çevre dostu polimerlere odaklanan araştırmacılar kolay işlenebilir, düşük maliyetli, yüksek dayanım göstermesinden dolayı PLA'ya yönelmiş durumda ve PLA'nın kemik doku mühendisliği uygulamaları oldukça mevcut. Peki PLA nedir? PLA biyobozulur olduğundan bahsettik. Bu da ve yenilenebilir kaynaklardan elde ediliyor. Mısır, şeker, patates ve benzeri yenilenebilir kaynaklardan elde ediliyor. Yüksek mekanik dayanım gösteriyor. Biyouyumlu olması zaten toksik özellik göstermemesi istediğimiz bir durum. Biyobozulurluk da tabii ki kendisi bozulacak ve yerini doğal kemik dokusuna bırakacak. Ve kolay işlenebilir olması tercih sebeplerinden. Peki neden PLA? PLA çözündüğünde biyobozulur olduğundan dolayı hidrolizinden sonra su ve karbondioksit moleküllerine dönüşüyor ve bozulduktan sonra vücut içerisinde toksik bir yapıya dönüşmemiş oluyor. Termal işlenebilirliği, mekanik özellikleri diğer polimerlere göre de avantajlı durumda. Bozulma oranı hasarlı kemiklerin iyileşme süresiyle eşleşebilmekte. İmplante edildiğinde konakçı kemik hücreyle biyolojik etkileşimlere girebiliyor. Ve tabii ki petrol bazlı bir polimer değil, biyobazlı, biyobozulur bir polimer olduğu için de daha az enerji kullanılıyor. Yine kemik iskelesi olarak PLA'nın uygulamalarından birkaç çalışma ekledim, onlardan bahsedeceğim. Yapılan bir çalışmada 5 farklı gözenek boyutuna sahip doluluk oranları ve gözenek boyutlarına göre %50, %60, %70, 80 ve 90 oranlarında 5 farklı gözenek boyutuna sahip mezenkimal kök hücre ekili 3B baskılı PLA iskelelerinin kemik doku mühendisliği için yapısal ve morfolojik karakterizasyon araştırması yapılmış. Araştırma sonrasında burada sen görüntüleri ne koydum? Gözenek boyutları gittikçe küçülmüş, yani sıklaşmış ve semanalizleri. Sonuç olarak kortikal kemik normalde 15-25 gigapascal aralığında kortikal kemiğin modülü 15-25 gigapascal aralığındayken süngerimsi kemiğin modülü 0,1-2 gigapascal aralığındadır. Bu çalışmada elde edilen modül değerleri kortikal kemiğe göre daha düşük olmakla birlikte süngerimsi kemiğin doğal yapısına benzer olduğu görülmüştür. Gözenek boyutu arttıkça da mekanik dayanım azaldığı görülmüştür. Dolum oranı arttıkça iskelelerin yağ modülü değerlerinin arttığı gözlenmiştir. Mekanik özellikleri sadece yapısal sağlamlık kazandırmakla kalmayıp aynı zamanda kök hücrelerin büyümesini ve farklılaşmasını etkilediği bilinmekte. Burada gözenek büyüdükçe neden mekanik dayanımın azaldığını açıklayacak olursak da daha önce gözeneklerin boyutunun belli bir optimum değerde olması gerekir ki hücreler daha rahat etrafına yapışabilsin, birbiriyle iletişim kurabilsin. Bu sebeple gözenekler küçüldüğü için hücrelerin hareket etme yeteneği de azalıyor gibi diyebiliriz. Yine başka bir çalışmada PLA'nın içerisinde metal malzeme olarak titanyum alaşım takviyesi konularak yine 4 farklı dolu içerik oranına sahip saf PLA %3 katkılı, %6 ve %9 katkılı titanyum alaşımlı iskeleler elde edilmiş ve bunların mekanik, fiziksel, termal, biyolojik açıdan araştırılmış. Yine buradaki görsele göre saf PLA'dan 9 katkılı titanyum alaşımlı olan iskelelere göre saf PLA'nın daha pürüzsüz, titanyum katkısının arttıkça daha pürüzlü hale geldiği ve fazla çiziklerin oluştuğu tespit edilmiş. Ve optimum olarak %3 ila 6 arasında titanyum katkısı olan kemik iskelesinin basınç modülünün ve basınç dayanımı normale göre daha çok arttığı görülmüş. Yine başka bir çalışmada da PLA'nın biyo uyumluluğunu ve mineralizasyon kabiliyetini artırmak için, iyileştirmek için inci tozu katkılı bir çalışma yapılmış. Saf PLA, kemik dokusu, kemik iskelesi, %1, %2 ve %3 inci tozu ilave edilmiş. Ekstradan kemik iskeleleri üretilmiş. İnci tozu hidroksiapatit birikimini ve hücre kültürünü desteklemek için kullanılmış. Yine çalışmanın sonucuna göre bu görsellerde de anlıyoruz ki saf PLA'nın üzerinde hidroksiapatit birikimi en azken inci tozu arttıkça, katkısı arttıkça hidroksiapatit oluşumu daha fazla olmakta ve zaten bu da istenilen bir durum. Kemikleşmenin başladığı ve meydana geldiği, hızlandığı anlamına geliyor. Orada bahsetmiş olduğum biraz ama işte çalışmanın sonucuna göre de saf PLA'nın yüzeyi çok pürüzsüzken PLA ve inci tozu katkısı arttıkça pürüzlü hale gelmiş durumda. Hidrofiliklik artmış durumda. Mineralizasyon işlemi hidroksiapatit parçacıklarının numara yüzeylerinde birikmesine neden olmuş ve PLA inci iskelesi hidroksiapatit ile tamamen kaplanırken yalnızca kısmen saf PLA iskelesini kaplamış durumda. Son olarak da ticari olarak kullanılan ürünleri koymak istedim. Bunlar kemik grefleri. Osteopor ve osteomeş firmalarına ait, osteopor firmasına ait osteopor ve osteomeş kemik grefleri ve iskele yapısı. Bunlar da 3 boyutlu FDM ile üretilen ticari ürünler arasında. Sonuç ve gelecek perspektifi, yani PLA'nın biyobozulur olması, işlenebilirliği, biyouyumluluğu, yüksek mekanik özelliği nedeniyle biyomedikal alanda çok sık kullanıldığına değindik. Ve son zamanlarda eklemeli imalat teknolojisinin de artık kullanılmasıyla, hayatımıza girmesiyle PLA'nın ya da diğer polimerlerin bu alanda sıkça kullanılacağı görülmekte. Ayrıca şöyle bir öneri de olabilir. Uygun kemik bölgesine ait malzemeyi ve tasarımı seçebilecek yapay zeka malzeme seçim ilişkisi kurularak akıllı seçimler yerine getirilebilir. Yine bir sorun olarak kalan biyobozulur malzemelerle üretilen kemik iskelelerinin bozulma hızı ayarlanabilmelidir aslında. İnsan vücudu üzerinde uzun vadede olumsuz etkilere sebep olabilen implant malzemelerden kaçınmak için biyobozulur polimerlere yönelilmiştir. Ancak bunun da yani erken ya da geç bozulmasından kaynaklanan mikro malzeme davranışları analiz edilmeli ve değerlendirilmelidir. Ekstradan ben bir 3-4 tanesini koydum ama PLA ile diğer biyopolimerlerin birlikte oluşturacağı kompozit kemik iskelesi seçenekleri artırılabilir ve performansı iyileştirilebilir. Teşekkür ederim dinlediğiniz için.
Teşekkürler Melisa. için. Öğrencimize sorunuz var mı? Buyurun hocam.
Mesela tebrik ediyorum. Gayet güzel hazırlamışım, gayet güzel toparlamışım. Ben bu PLA'nın biyo uyumluluğu konusunu merak ediyorum. Yani çok iyi biliyoruz ki biyo bazlıdır, biyo bozulur ama biyo uyumluluğu konusunda ne söyleyebilirsin?
Biyo uyumluluğu olması aslında vücutta toksik etkileştiğinde toksik etki bırakmaması aslında. Toksik etki bırakmadığı için biyo uyumlu diyoruz. Ve PLA gerçekten de vücut içerisinde bulunduğunda su ve karbondioksite ayrıştığı için bu vücudumuz için en azından uzun vadede böyle bir kötü etkisinin olduğunu okumadım. O yüzden su ve karbondioksite parçalandığı için biyo uyumlu olarak gördüğümüz bir biyopolimer. Ve zaten yenilebilir kaynaklardan da elde edildiği için bu şekilde açıklayayım. Rica ederim.
Çalışmalarınızda PLA mı kullanacağız?
Evet, yani daha önce yüksek lisans tezimde PLA'da hibrit malzeme üretimi yapmıştım. Doktora tezim bilgilerindeydi ama yeterli değil zaten. Ama kemik dokusu çok ilgimi çeken bir konu. Çalışmak istedim.
Hidroksapatitlerle de çalışıyorsunuz. Evet. Yani biz sapatitle çalıştık tabii kendi alanımızda çalıştık. Tıbbi alanda bunu absorban olarak kullandık, kompozit haline getirdik ama hani çalışırken gördük ki gerçekten hidroksit apatit birçok alanda kullanılır. Çünkü biliyorsun içerisinde işte kalsiyum olduğu için zaten kemik dokusuna da çok uyumlu. O tarz çalışmalar yapıyor. Hem de kendimiz yani doğal yollarla da elde edebileceğimiz bir şey bu. Yumurta kabuğundan ya da işte tavuk kemiğinden ya da herhangi bir şeyden de hani deneme amaçlı olarak yapılabilecek bir malzeme. Başarılar dileriz. Tebrik ederim. Teşekkür ederim. Evet değerli katılımcılar, bu oturumumuz bitti. Şimdi evet çay kahve molası var. Daha sonra devam edeceğiz tekrar. Teşekkür ederim. Ben teşekkür ederim.
In this session, we are going to have 3 papers and 1 invited speech. And I want to start with our inviting our invited speakers to the stage, Dr. Iqbal Gözde Kaptanoğlu, to speak about polymers in radioactive water treatment applications and sustainability. And because I don't have the resume here, please introduce yourself, and we are listening to your speech. Thank you, sir.
Thank you very much. Hello, dear participants. My name is İkbal Gözde Kaptanoğlu, and I'm an assistant professor in Institute of Nuclear Science, Department of Nuclear Technologies at Ege Üniversitesi, İzmir. I would like to start by expressing my gratitude for the opportunity to present at this symposium. A special thank you to organizing team for their hard work in bringing us all together. In today's presentation, I will be discussing polymers in radioactive water treatment, applications, and sustainability. Before we dive into the technical aspects, I would like to begin by briefly introducing my university and institute. To begin, to share a bit where I work. Ege University, established in 1955, is a prestigious institution with a rich history of academic excellence. The Institute of Nuclear Sciences at Ege University is dedicated to advancing research in nuclear science. Our institute focuses on 3 primary domains, which are nuclear sciences. Research includes radiological studies, radiation measurement system, radon applications, and radiometric techniques for studying radioactive minerals. Second one is nuclear technology. This is my department. Key areas include uranium and thorium recovery, radioactive waste management, the development of new solvents. And the third one is nuclear application department. This department focuses on the design of new imaging and therapeutic agents, synthesis of radiolabeled nanoparticles, and applications in nuclear medicine and industrial settings. In our department, sustainability and innovative approach to radioactive water treatment are the key research priorities. Okay, water is a vital resource, exists in 3 states, solid, liquid, and gas, and it's found abundantly across our planet, whether in the atmosphere, oceans, or underground. However, we primarily depend on groundwater stored in soil and rock, and surface water from rivers and lakes for municipal, industrial, and agricultural needs. Importantly, water resource availability fluctuates significantly due to geography, climate, and land use, creating an uneven global distribution and impacting clean drinking water access. As illustrated in the figure, 11% of the global population lacks safe drinking water, and inadequate sanitation affects 1 in 3 people worldwide. Given the current energy landscape, the importance of nuclear energy is on the rise, especially as we see a decline in fossil fuels. In 2020, nuclear power contributed about 10.3% to global energy production, and that number jumped to 18.9% by 2021. This shift is crucial for energy sustainability, but it also brings the significant responsibility of managing large volumes of radioactive wastewater effectively. As the trend towards nuclear energy is expected to continue, we must seriously consider how to manage radioactive waste. Improper disposal of this wastewater can have lasting effects, particularly in coastal and marine environments. The harmful isotopes present in untreated wastewater could lead to ecological devastation and serious health issues for communities relying on these water resources. Therefore, it is essential that we develop innovative and efficient treatment methods to mitigate these risks. The critical importance of radioactive waste management was highlighted by 2011 Fukushima Daiichi nuclear power station disease. During this event, a variety of radioactive isotopes were released into surrounding water bodies, and radionuclides were subsequently detected in several aquatic environments. In such a catastrophic incident, the marine environment often becomes a primary focus, as many nuclear plants, as you know, are situated near coastal areas. Effective treatment and management of nuclear wastewater can be achieved through chemical, physical, electrochemical, or biological process, which either concentrate or separate radionuclides from wastewater. At the time of Fukushima disaster, nature control strategies and treatment technologies for radioactive wastewater were not readily available. However, significant advancement in the treatment of radioactive wastewater have been made between 2011 and 2023. Consequently, numerous studies have reviewed individual purification technological aims at addressing this challenge. Water can be contaminated with radioactive elements from a variety of sources. Natural sources, which are radioactive elements like uranium and radon, are naturally present in Earth's crust. Therefore, these can reach into groundwater, especially in areas with high natural radioactivity. And the second one is mining and ore processing. Mining activities, especially for uranium, can release radioactive particles into nearby water resources through waste disposal or accidental leaks. The third one is nuclear power plants. While generally safe, nuclear plants can discharge low levels of radioactive materials, especially if there are accidental leaks affecting local water quality. Nuclear weapon testing. In the past, nuclear tests released radioactive particles into the atmosphere, which eventually settled in the soil and water bodies, impacting the ecosystems. Nuclear waste, we can say, improper disposal of nuclear waste poses risk of leaching radioactive elements into water sources, which is a significant environmental concern. And the sixth one is coal ash. Coal combustion leaves ash with small amounts of radioactive material. If it is not properly managed, this can contaminate nearby water bodies. And in nuclear incidents like Chernobyl and Fukushima, it has shown how nuclear accidents can release large amounts of radionuclides, radioactive materials, into the water system with long-lasting effects. Each of these sources contributes to radioactive contamination in water, creating various environmental and health challenges. In this slide, I show several radioactive elements, common radioactive elements. These radioactive elements are significant due to the environmental impact and the effect of human health. This includes uranium, thorium, radium, strontium, cesium, etc. One critical factor is assessing their hazard level is half-life of their isotopes. For instance, uranium is essential nuclear fuel resource and a key component in radioactive liquid phases. Interestingly, naturally occurring uranium poses minimal environmental threats. And radium, however, stands out as the most hazardous isotope found in tailing. Thorium is widely used in various industrial and medical applications. It is also proposed as a fissile material for nuclear energy production by generating uranium-233 from thorium-232. Now we look at the cesium, strontium, and cobalt. They are considered especially dangerous to human health. Why they are dangerous? They have long half-life. Cesium lasts for 30 years, strontium 28 years, and the cobalt is over 5 years. These isotopes are highly transferable, soluble, and easily absorbed by living organisms. Cesium and the strontium are particularly concerning because of their chemical similarity of potassium and the calcium, allowing them to enter the human body more easily, posing long-lasting radiological risk to both environment and human health. Radioactive elements in water pose serious threats to both aquatic ecosystems and human health. These contaminants affect not only rivers and lakes, but also groundwater, making their way into our food and water resources. One major issue is bioaccumulation. Radioactive elements build up in plants and animals over time, especially in marine and terrestrial food chains. As these elements move up the food chain, they stay in organisms for long periods, which raises cancer risk and other health issues both for wildlife and humans. Because these contaminants are persistent and remain in ecosystems for long duration, effective removal techniques are crucial. Without proper treatment, radioactive elements continue to endanger ecosystem and human populations, highlighting the need for sustainable removal methods. As I said, uranium, a key element in nuclear power generation and weapon production, is also a major pollutant in nuclear facilities. Its radioactive and toxic nature poses several health risks, including kidney and liver damage, cancer, cardiovascular diseases, and even death with prolonged exposure. This makes uranium is one of the most dangerous substances released during nuclear accidents or mishandlings, let's say. Effectively, managing uranium contamination is critical for both environmental protection and public health safety. While various methods like precipitation, membrane filtration are effective methods, absorption stands out for its low cost and scalability. The absorption process involves the transfer of radionuclides from the liquid phase, let's say wastewater, to the solid phase absorbent. Radionuclides in aqueous solutions are attracted and bind them with the surface of the absorbent material. This process is facilitated by the functional groups present in the absorbent surface, which can form electrostatic attraction or chemical bonds with the radionuclide ions. Conventional forces involved in the absorption include electrostatic interaction, like van der Waals forces, and chemical bonding. A broad range of absorbent materials has been explored for the removal of radionuclide, including natural materials like clay minerals, zeolites, activated carbon, as well as engineered materials like MOFs, nanomaterials, and composites. Each type of absorbent offers special advantages in terms of selectivity, capacity, and ease of regeneration. When we see in the figure, research on radioactive wastewater treatment is becoming increasingly important, shown by steadily rising published studies in this field. This trend highlights an urgent need. We must find ways that either safely reuse treated nuclear wastewater or recover valuable radionuclides. To address this challenge, a variety of methods have been explored, including chemical, physical, biological, and electrochemical techniques. However, as you see in the figure B, two methods, absorption and membrane separation, have drawn the most attention due to their effectiveness in removal of radioactive contamination. Natural polymers extracted from sources like microorganisms, plants, and animals have long been used in biomedical fields, from pharmaceuticals to tissue regeneration. This figure shows examples of these natural polymers and their structures. In contrast, synthetic polymers are artificially produced in labs and classified into categories like thermoplastic, thermosets, and elastomers. Some common examples include polyethylene, polystyrene, and polyvinyl chloride. These polymers typically derive from petroleum-based monomers and produced in the controlled environments using specific initiators and catalysts to facilitate reactions. Natural and synthetic polymers both play a significant role in water treatment. Arginate, ketosane, and the polyvinyl PVA are the popular choices due to their binding properties. By functionalizing these polymers, we can improve their ability to capture radionuclides, enhancing water treatment efficiency. Future research should focus on increasing the selectivity and the stability of these materials, ensuring they perform well in various environmental conditions. Polymers are highly effective in treating radioactive wastewater due to several key properties, which are high selectivity and capacity. Polymers can be tailored to target specific radionuclides, allowing for efficient removal even at low concentration. Ease of functionalization. They can be chemically modified to improve binding sites, enhancing their effectiveness in capturing radioactive particles. High surface area and porosity. These features increase the polymer's capacity to absorb contaminants, making them ideal for wastewater treatment. Chemical and mechanical stability. Polymers are durable, which means they maintain their structure and performance under harsh conditions. Environmental compatibility. Many polymers are biodegradable or can be environmentally friendly, reduce concerns. And the last one is economic and operational benefits. Polymers are often cost-effective and easy to work with, making them practical for large-scale applications. These advantages make polymers versatile and valuable materials in developing sustainable solutions for radioactive wastewater treatment. Up to this point, I have provided a general overview of the increasing research interest in radioactive wastewater treatment and the commonly explored methods in this field. Now, I will focus on the specific contribution in our work in advancing this area. Our research emphasizes that use of polymer-based solvents for the effective treatment of radioactive wastewater. In the following slides, we will discuss the efficiency, sustainability potential, and the environmental impact of the methods we have developed. Our first approach involves the preparation of innovative alginate capsules that enclose diatomite and organic extractants for targeted lanthanum uptakes. I will provide a brief overview of this study, including the method of capsule preparation, its effectiveness of the capturing lanthanum, and the potential benefits for sustainable water treatment. Our study aims to synthesize calcium alginate composite beads using combination of trioctylamine TOA, tributyl phosphate TBP, trioctyl phosphate oxide, topo, and diatomite to effectively separate lanthanum ions. Lanthanum is widely used in superconductors, ceramics, glass, magnets, electrochemical applications, and as a catalyst due to its unique metallurgical and electrical properties. With a global usage of lanthanum, around 200 metric tons per year, and its presence in the environment is a growing concern as it has potential carcinogenic effects, impacting cell membranes and possible effect in the reproductive and nervous system. To address this challenge, we are using alginate as a base material in our composite, which offers several advantages. Alginate allows for easy encapsulation and cost-effective and high acid resistance. It can also exchange ions, making it particularly effective for binding heavy metals and certain radionuclides. This combination of materials should improve the efficiency and the selectivity of lanthanum ion separation, addressing both environment and health concerns. Polymer impregnation in this study, we are focused on it, with extractants offer some key advantages in radioactive wastewater treatment. Simple preparation process. This method is straightforward, making it easy to implement the various applications, and broad applicability allows us to work with a wide range of selective extractants, making it versatile for different contaminants. And ease of separation. Once the treatment is complete, separating of the solution from the resin is simple, streamlining the process. However, there are some also challenges, which are steric hindrance. Sometimes the structure of the polymer can block certain extractive molecules, reducing their accessibility or limiting extraction efficiency, and the selectivity issues. Extractants can become inactivated over time, which may reduce their ability to selectively target specific conditions. These factors highlight the balance between ease of use and technical challenges we need to address more effective extraction. In this study, composite beads were prepared by adding TBP, topo, and TOA to sodium arginate diatomite mixture. The beads were then characterized using scanning electron microscopy to examine their surface morphology, while FTIR was employed to analyze their chemical structure. These results show that the maximum uptake capacity of lanthanum is 146 milligram per gram, with an impressive absorption efficiency around 90.70%, 90-70% in dilute solutions. Additionally, the absorption behavior followed the Langmuir model, indicating a uniform absorption process. Finally, thermodynamic parameters, including enthalpy, entropy, and Gibbs free energy, were calculated to provide deeper insight into the system's thermodynamic properties. Some images reveal that key structural features across the different materials. Calcite diatomite, in the shown in figure 1, is characteristic skeletal structure and pores, while pure alginate biopolymer in figure B, 1B, exhibit clear surface topography. When diatomite is added to alginate, that we can see in the figure 1C, we see the preserved fossil-like structures from diatomite in the composites. For the functionalization composites, alginate with topo diatomite, TBP, and TOA diatomite all display diatomite porous structures on surface, confirming successful material impregnation. And the second study of the focus on the removal of lanthanum and cerium from aqueous solutions using specially developed Kitosan functionalized magnetic pectin composites. This approach leverages the magnetic properties of the composite for easy separation, along with Kitosan's natural affinity for binding metal ions. I will walk through the synthesis process, its absorption efficiency, and the potential for practical applications in radioactive wastewater treatment. In this study, we worked with two key materials, which are pectin. First one, pectin is a biocompatible and enhanced the chemical binding, and Kitosan is the second one, a natural biopolymer widely used in water treatment. True, it has some limitations, such as low solubility and mechanical strength. Our objective was to synthesize and characterize iron pectin chitosan nanocomposite to evaluate its efficiency in removing lanthanum and cerium ions from the solution. To achieve this, we examined how factors like pH, ion concentration, contact time, and temperature influence removal efficiency. Additionally, we conduct kinetic and thermodynamic and isotherm studies to gain a deeper understanding of the absorption process. Chitosan is a natural cationic biopolymer derived from chitin. Chitosan has the ability to act as an absorbent in different forms, which makes it suitable for use and removal agents for harmful pollutants. Nevertheless, some inconvenience has been found when used alone as a difficulty to separate these pollutants after the removal process and decrease and the degradation in absorption efficiency, with the repeated use and the poor absorption towards certain pollutants. For this, further studies were carried out to overcome this inconvenience and improve the absorption character of chitosan. Indeed, the strengthening of chitosan and the improvement of its absorption properties can be achieved through the association with other materials such as polymers, clays, or zeolites, and this leading us the appearance of composite materials with new functional groups and novel properties. In this study, we synthesized magnetic pectin chitosan composite using co-precipitation method, and we started briefly by adding pectin solution dropwise to the iron chloride in hydrochloric acid, followed by the slow addition of sodium sulfide and ammonia. After stirring the mixture for 24 hours, it was washed, filtered, and dried at around 600 degrees Celsius. To functionalize iron pectin composite chitosan, the ionized water and the ethanol were incorporated, and the final mixture was dried under the infrared lamp. These steps were carefully optimized to achieve these desired properties in the composite material. Chitosan is a biodegradable polysaccharide from marine sources, provide excellent absorbent properties in the study, and it's both cost-effective and environmentally friendly. Despite these advantages, chitosan has limitations such as low mechanical strength and limited solubility in acidic media. By modifying materials such as cross-linking, true cross-linking, we improve its stability and mechanical resilience. This synthesis approach combines chitosan's natural benefits with strength and magnetic pectin, producing as a scalable, eco-friendly composite with enhanced absorption properties, no toxic chemicals involved. In another study, the third one, we focus on the repurposing PET polyethylene tetrabutylate base as an absorbent for removing cerium and strontium ions from aqueous solutions. PET is widely known as in plastics non-biodegradable and contributes significantly to environmental waste. By modifying PET waste into the effective absorbents, we aim to address both environmental pollution and water contamination issues. This approach not only reduces plastic waste, but also provides a cost-effective and sustainable solution for treating water contamination and radioactive elements like cerium and strontium. In this study, we focus on two major environmental concerns: radioactive isotopes and plastic waste. Strontium-90 is a highly radioactive isotope with a long life, around 29 years. It accumulates in bones and teeth, posing significant cancer risks. And similarly, cerium-144 is a fission product found in nuclear wastewater. This chemical is similar to actinides, making its removal critical. On the other hand, the global production of plastics, especially polyethylene tetraflate, has reached alarming levels. And in 2020, it's around 334 million tons produced. And 60% of all plastic waste remains in the environment. PET is a non-biodegradable polymer and taking over 180 years to degrade, which amplifies its environmental impacts. Recycling PET through chemical and physical methods not only help mitigate the environmental issues, but also conserves petrochemical materials. Understanding the significance of these materials and their environmental implications, it highlights the needs for effective treatment and recycling strategies. In this study, first, really easy process. First, PET-based bottles were collected, cut into small pieces, and cleaned with nitric acid, rinsed with pure water, and dried in the oven. For phenol modification, PET was dissolved in phenol in around 100 degrees Celsius, 25 minutes, so fast. This mixture when solidified in a petri dish and washed in light water and dried overnight. The dissolution mechanism involves the relaxation of PET chains in phenol, balancing the polymerization and fragmentation. Heat-induced decomposition forms radical and the fragments with radical ends, making the modified PET more reactive for absorption application. This is the last study, is an ongoing project focused on reduced graphene oxide, zinc oxide, shortly RGO zinc oxide nanofibers for enhancing the absorption for uranium from aqueous solutions. These nanofibers are particularly effective due to their high surface area and porosity, making them an ideal candidate for radionuclide removal. Using response surface methodology, RSM in short, we optimize critical parameters such as pH and the temperature to maximize absorption efficiency. The innovative aspect of this study lies in the synergy between graphene oxide, reduced graphene oxide, and the zinc oxide, which not only boosts the absorption capacity but also prevents the aggregation of the nanomaterials, enhancing their long-term stability. This approach has the potential of scaling up. The further research could explore its application in nuclear facilities and other industries dealing with heavy metal contaminants. As I mentioned earlier in the presentation, uranium is a byproduct of mining, processing, and nuclear power activities, posing significant environmental and health risks due to its radioactive properties. The presence of heavy metals in water is a major concern, creating both ecosystem and human health. Therefore, there is a critical need for effective removal methods to purify water contaminated with radioactive materials. Among the various techniques, absorption stands as a simple, cost-effective solution for reducing metal concentration in contaminated water. The use of nanofibers in this area, with high surface area and porosity, makes them ideal for this process. However, materials like graphene and its composites, while offering excellent surface area for absorption, it also tends to aggregate due to van der Waals force, which can limit their efficiency. In this point, this is where reduced zinc oxide, reduced graphene oxide, zinc oxide nanofiber composite comes in. By combining zinc oxide with reduced graphene oxide, we significantly increase the surface area while preventing aggregation. This composite shows great promise for high absorption potential, particularly for heavy metals like uranium, making it a promising solution for radioactive wastewater treatment. In this study, we use electrospinning technique to synthesize nanofibers. As discussed many sections, electrospinning applies strong electric fields to polymer solution, creating nanofibers with high surface area and porosity. It's ideal for absorbing heavy metals like uranium. By combining reduced graphene oxide with zinc oxide, we enhance the nanofibers' absorption capacity and prevented aggregation, making them suitable for environmental application. Electrospinning is a versatile method used across various fields, including medicine, drug delivery, tissue engineering, pollution removal, filtration, even food packaging. This highlights its broad potential in both technological and sustainable applications. Before concluding my presentation, I would like to briefly highlight the work in our colleagues in nuclear application departments. They recently conducted a study titled Design of 99M Technician Radio-Labeled Gemcitabine Polymer Nanoparticles as a Drug Delivery System and in vivo applications. This research focused on developing radio-labeled polymeric nanoparticles for targeted drug delivery, especially using gemcitabine for cancer treatment. A significant advantage of polymeric nanoparticles is their ability to trap into the drug within a solid matrix, which protects in form of degradation and enhances its stability. Their work underscores the broad potential of polymers not only in the medical applications but also in the nuclear field, demonstrating the versatility of polymer-based technologies beyond the wastewater treatment. In conclusion, the increasing production of radioactive wastewater driven by the expansion of nuclear energy underscores the urgent need for effective treatment methods. As we have seen, improper disposal of radioactive water poses serious environmental risks, highlighting the importance of developing advanced scalable technologies for its management. Our research, particularly in polymer-based sorbents in nanomaterials, contribute to these efforts by offering promising solutions for the removal of radionuclides from contaminated water. Looking ahead, it's crucial that we continue to develop efficient and scalable treatment technologies for radioactive wastewater, especially as the global demand for nuclear energy rises. Innovative solutions are needed to manage radioactive contaminants effectively and safely. One promising avenue for this for the use of nanomaterials such as zinc oxide nanofibers, which offer high surface area and porosity and heavy metal absorption. These nanostructures have the potential to significantly enhance the efficiency of wastewater treatment. Moving forward, research should focus on optimizing these materials for larger scale applications. Additionally, it's essential that future advancements in this field prioritize sustainability. We must develop long-term strategies for wastewater management that not only treat contaminants effectively, but also minimize environmental impact, ensuring that we are addressing the challenge of radioactive contamination in an environmentally responsible way. And thank you all for attention and the opportunity to share our research. I hope this presentation has provided valuable insight into challenges and potential solutions for treating radioactive wastewater. Thank you again.
Thank you so much, Balujan. It was a very nice presentation. Nice enough. We are ready for questions from our audience. Please, if there is any question. So let me start with some questions. You are telling that one of the methods for removing radioactive elements is absorption. And with the absorption, we are absorbing the radioactive elements, but we are ending up with loads of materials with the elements, radioactive elements in them. We can separate them, but at the end of the day, they are still dangerous to us. So what can we do with the mass containing with the elements after absorbing to the solid part?
Thank you for your question. As far as I understand, you are asking how to store the radioactive material after absorption.
Exactly, yes.
There are several ways to collect them. One of them is vitrification. You can vitrify it solid parts, including such as radioactive materials like when they are vitrified, or concrete. You can use concrete and build it like that with the materials. And even you can vaporize first of all the water parts, and we can remove the liquid parts, including radioactive elements. This kind of ways we can do it in a large scale.
So storage is another problem.
Yes, storage is another problem.
If we want to get rid of this part of the problem, for example, we want to add something to the polluted wastewater and completely deactivate the radioactive element and leave them in the environment. Is it possible?
But you are using an absorbent material in the system. So
No. I'm asking anything, for example, any idea. Is there any method, even theoretically, to be viable for just adding something to deactivate them and leave them or in a neutralized form in the environment? Is there any way?
As far as I know, there is no method like that, but there is a future that can be like that. But there are lots of materials, smart materials, materials or natural materials, we can use it, but at the end of we can remove it. But the thing is desorption. After absorption, desorption, we can use the same material again, so it's help us to cost effective way. But in your question, as I know, there is no material like that.
So we wish for that one day maybe somebody. And my next question was for the polyester. In your experiment, you dissolve polyester in phenol, and after that produce some layer or some, for example, new product out of that, which is still polyester, and it is water insoluble. So how can it absorb radioactive elements?
Polymer has low absorption capacity, but
yes.
We use polyethylene tetracycline because it's everywhere is polyethylene tetracycline, exactly. And it's not easy to degrade.
You're right.
That's why we had some modification, like phenol modification, to increase absorption capacity. But still, we can work on it, we should increase the absorption capacity because it's not enough if you compare the other literatures. Exactly. But the importance of this study is we use the waste material, head waste, and even it works. But we can increase the absorption capacity to modify other elements.
Okay, that's
Thank
good.
you very much.
Thanks, sir. Any other questions? Thank you so much for the presentation. Okay, we are moving on to our second paper, which is a review paper on functional nanostructure for, can we have it here, please? Functional nanostructures for atmospheric water harvest, AWH, in low humidity regions. It is going to be presented by Mr. Bustani. He is a part of research team between Qatar, from University of Doha for Science and Technology, Istanbul Technical University, and Akdeniz University. So we are waiting for him to start his presentation. Please.
Hello everyone, thank you. And I want to present our review about functional nanotexture for atmospheric water harvesting, AWH in low humidity region. Importance of the water is a molecule separating life and death, and water is essential life. Freshwater resources are very limited, and distribution of the water is uneven around the world. Many areas are facing several water shortage, and water scarcity or water shortage is a critical global issue, and with significant impact on drinking, sanitation, or irrigation. And it is estimated that by 2050, nearly half of the world population will live in a water-stressed region. Okay, the Earth is often called the blue planet because of its abundant water, and how much water is on the Earth compared to the air. This here is all of the water in the Earth, and this here we have this much water in the Earth. From this water, 97.5% of this water is solid, and the water from the ocean. And from this much fresh water, we have very little water for using as a fresh water, because a lot of that is in the groundwater, and another one of them is in the glaciers and snow, like the ice. And from this much, we have 67% of this much is in the lake, and 12 in the soil, and this much of water we have in the excess is atmospheric water, and this much is 13 trillion liter water, and this is available in the air, and we can harvest that from the air. The key fact is have 3 trillion liters of water in the atmosphere, and our challenge is converting this air moisture to the liquid water as a fresh water for drinking. And how can we harvest the air moisture as a liquid water. This year, atmospheric water harvest method is our solution for capture this water from the air. And AWH system or atmospheric water harvesting have a lot of advantage for us because this method being geographical, versatile, and implementable at the both highly populated and central setting. And AWS system help us for promote idea of water in and we always have water available in atmosphere at any given time, which is constantly naturally replaced, renewable, and sustainable. And absorption base of this method are very economical and able to operate at a wide range of environments related humidity and temperature. We have many branch of this category of atmospheric water harvesting. The first one is condensation-based AWH, and this is contains dew and fog harvesting, and the cooling technology and the membrane technology. Cooling technology has passive and active cooling, and another method is this desiccant-based AWH. It contains solid and liquid desiccant composite system, and our product for use in this year from desiccant, and we have solar driving system, thermal AWH, integrated integration with the desiccant. This is vapor compression and its filter effect. This is under condensation. We have a lot of this is what harvesting. This is the fog harvesting in the mountain, and this is the fog harvesting in the yard, and harvesting the water from the cave. Water vapor condensation compared to the harvesting water from fog. This have some problem because we need high humidity area for capturing the water from the air, and we should have a big size of the water droplet for capturing this fog and compared to the water. And from the harvesting water with the dew point, this is there's in the nature, and we can see maybe in the spider network. And another method is active refrigeration of the humidity, like the air conditioner in the home. And this is consuming a lot of energy and in a higher than 40% emissions. And at the last, we have the desiccant base for harvesting the water, and this consists of two stages. Usually in the absorption stage and in the absorption stage. And we can use a lot of material in this field. Maybe we can use gels and desiccants, but this is not very efficient because you can absorb the water, but for desorption you will have a lot of problem. Absorption material compared to the physical absorption material, chemical absorption, composite absorption, and polymeric absorption. And from physical absorption, we have silica gel, jelly, aluminum silica, aluminum phosphate. And from chemical absorption, we have CO2 and LICS, and we have composite absorbents like composite of activated carbon, and a lot of composites of this absorbent. And this here we have a polymeric adsorbent. It's converted to metal organic framework and polyethylene and the hydrogels and covalent organic framework. They're new and for various characteristics affecting the performance of an adsorbent-based evaluation compared to the intercrystal activity, fusivity, absorption of the lagging porosity, formula and crystal size, and so on, etc. Metal organic frameworks. This is our selection for this. Most are class of high porous polymer and consisting of metal ions or glass cell. With the metal ion is here and is here, and we have these metal ions coordinated to organic ligands. And organic ligands, it's another name of this is linkers. Actually, we have the crystal material in this here. When have a lot of core in this material, and we can use this core for absorption and absorption. The first one have invented this material is the Dr. Mariati from Berkeley, and this you can find this material from 2000, and this material have a good evolution in the year from now. The properties of the MOFs, metal organic frameworks, we have chemical properties, absorption properties, environment response, functional properties, and physical properties, and structural properties of this material. And we can use one by one of this material for harvesting gold. Maybe high surface area of this material, large core volume of this material, tunable core size of this material, and the shape of this material, have a structure, a crystalline structure of this material. All of these help us for using this material for water harvest. And the application of the MOFs is very extended, and we can use this material for energy application like catalysts for this reaction. And you can use this material as energy storage, hydrogen storage, thermal energy storage, and for clean energy technology, like fuel cell and solar energy converter. And you can use this material for sensing detection, like chemical sensor, gas sensors, burning solid, and biological sensing. And you can use this material for environment application, gas storage separation, this industrial for CO2 capture, and we can use this material for water application as a water harvesting and water purification with the for this material, and wastewater treatment. We can use this material for air purification like mask and or have air quality improvement and pollutant removal. We can use this material for medical functional application like drug delivery, because we have a lot of ore in this material, and we can change this ore with the change our ligand and the change cluster metal ions in this material in the synthesis process. And for the drug delivery, we can use all of this material and biological application like tissue engineering and another application. Water absorption from the atmosphere, but the moth.
Sorry, I think I will interrupt you. You just have more.
We have this moth, and this is have the progressing solution, and have a lot of advantage because we can absorb the water in the location, dry location, with the humidity, with the 10% humidity, and this is our advantage, big advantage. And in this material for water absorption, we have a lot of factors, like foresight, like flexibility, these frameworks, and the presence of the hydrophilic functional groups we have in this material can absorb the water, hydrohydroxyl and carboxylic and amine group in this material, and we have a lot of material, and all of this material can absorb the water. And the water absorption mechanism in the moth is we have physical absorption and chemical absorption in this material. And for physical absorption, we have van der Waals and hydrogen bonding and capillary condensation from this material. And in the chemical absorption, we have different coordination between water and metal substances, and the reason of metal oxide captured with water. And for this material, we cannot see the all of the holes and pores in this material, and we can see the specific surface area in this material with optical and electron microscope. And for research in this field, we need some device called the dynamic gas absorption. Can find all of the properties of this material. And this device gives us isotope for absorption, and we have a lot of absorption isotope, and this material can have a lot of this isotope for absorption in the water. But this device gives us absorb and desorption isotope in this field, and we have this curve from absorption of the water, this curve from the desorption of the water in this material. Factor affecting the absorption and desorption of this isotope depend on the moth structure, flow type, and the environmental condition in the material. What is the concept of the water absorption and desorption of moth? For desorption of the moth, moth absorb the water, maybe in this year, in the night, and is saturate. After that, the cover is here, and with the heat of the sun, we can dissolve the water from the moth, and this water can condense in the glass, and we can collect this water. This is a saturation, absorb and bring dissolve the water from this material. We have a lot of devices for absorption the water from the air. All of these devices is a moth base, and this is Waha, the company, a startup in the Berkeley, working on this material for absorption the water. And this company have a fourth generation of the device for absorbing the water, and at the first maybe 230 milliliters water per kilogram per day. After that, can get this much of water in the day, and the fourth generation in the 200 cycle can collect 40 per kilogram water for per kilogram of water. And what's the potential? The harvest can increase the water out of the maximum, and key is increasing the effective surface area, developing a new formulation maximum. And the solution is attaching this material with the fiber structure, and this is our target from the textile point of view in the attaching of the fiber structure. For giving moth powder the ability to quickly cool down and heat up, easier accessible to airflow. And we can, with the composition of the moth and fiber, increase the effective of communication between the water medium and the air. And we can enhance the mechanical and chemical stability of the moth. And we can giving the moth powder ability to move in our device, and we can have the scalability in industrial application and maximize the moisture absorption in our crops. And our strategy is a combination of the moth with the fiber and reduce the diameter of the fiber in this project. And our challenging is mechanical properties have issue for accessibility, because our polymer maybe is surrounded all of the moths and have a lot of problem. And for the dispersion of this material in some solvent, and the compatibility of this material with each other, and maybe have a lot of chemical stability problem and the mold stability. And we have a lot of methods for composition of the moth with the fiber. Like coating method, printing method, solvent testing, freezing, drying, solder method, and in situ polymerization for composite of the moth and polymer fiber. And we can mix the moth with the polymer, and we can use electrospinning method for this combination. And for selection, the process of the moth, the ideal moth, we should pay attention to high water uptake capacity of this moth, low Celsius, and low temperature, regenerative temperature, and have a good cycle stability of this material. We can see this here the inflection point of the moth, and in this year, this is the inflation, and this is the relative pressure of the. This is the absolute pressure, and this is saturation vapor pressure of the adsorptive at the experimental temperature, and this is the same from 0 to 100 relative humidity, and maybe in this for find and selection the group from 4 desiccant material we can use in this inflection point material like mold, and in this here for water harvesting we can use this material in this area, and we can use humidity control or humidity control of this material in this pressure. And this is our choice for mold in the project. This is the mold 303, and have a lot of benefits, and we can absorb the water and a lot of water from the arid area, and this is the mold synthesis, and our mold is easy synthesis, and the solvent for synthesis is water, and this is very good for us to use this material. And we have a lot of characterization in this material. For this material,
Sorry, can you
okay, this is the mold, and for the fiber, we can use the pan because we have a lot of porosity in the project, and the rigorous thing from this material. Okay, thank you very much.
Yes. Thank you, sir. Thank you, Dr. So, as far as I understood, you are going to mix mold with nanofibers or fiber structure, and after that, absorb water, the humidity from air, then to be able to release it again and condense it as liquid water. And this is going to be the future of water generation instead of being dependent on the, for example, local water sources like rivers, wells, something like that. Thank you so much. So, any questions, please? Please.
This is really, thank you very much for your presentation. This is a very, very interesting subject. If you make a breakthrough in the technology, you have a big, huge potential in this part of the world, in greenhouses. Excessive humidity is a big problem, creating disease problems, management problems, all sorts of problems. If you remove, there are technologies to, remove excessive humidity, but they are expensive, very expensive. If you do any, if you make any technology that remove humidity from the greenhouses very cheaply, you are the richest man, you will be the richest man in the scientific community. Thank you very much.
Yes. So, for the greenhouses, and for example, on top of that, it should be using low energy and very cheap. In that case, it's going to be a survival means for all the plants. So good luck. So, any other question? Thank you so much. Our third speaker is Dr. Mehdi Hassanzadeh from Yas University, Iran. He is an associate professor and working on nanotechnology field in textile. And the title of his paper is Functional Nanofibrous Filter. I'm so sorry, my voice does not help. Yeah, so functional nanofibrous filter material for particulate matter removal, tailoring properties and functionalities. Thank you so much.
Hello everyone, thank you for your nice introduction. And actually, at the second days of conference, at the last session, it was very difficult for me to present my topics for the audiences. I hope that you enjoyed this conference during these days. Okay, as we said, my topic is about the functional nanofibrous filter media for particulate matter removal. My interest is on how we can functionalize the nanofibrous structure and tune and maybe tailoring these properties with the additives that we add to the nanofibrous structure. So, let me check the table of content and outline. First,
speak a bit louder, please.
Yes. First, I introduce some important features of particulate matter, and after that about the functional nanofibers and the functionalization methods, and after that I will talk about how we can find some results and obtain results from the works of my colleagues and my students. You know that with the development of industrialization and fossil fuels combustion, air pollution has become a main concern about environmental pollution, and the air pollution are categorized into two types: the gaseous pollutants like NOx, SOx, and carbon monoxide and dioxide, and those are organic compounds. But the second category is about the particulate matter. Particulate matter is very important, and as they can deposit into the respiratory system of human, it's may cause a very concerning issue about the disease and can threaten the human health. According to their aerodynamic diameter, these particulate matter are categorized into three subsystems: coarse particulate matter, fine particulate matter, and ultrafine particulate matter. And you know that the fine particulate matter, as they have a large specific surface area and have a functional surface, they can deeply deposit within the tissue of human and make more concerning issue, and have and it may be produce a main problem for human health. How the nanofibers could filtrate or could remove these pollutants in the organic, in the gaseous state, charge-charge interaction, hydrophobic interaction, chemical bonding, and hydrogen bonding can make it possible to, for example, filtrate gaseous pollution. And in the case of particulate matter, there are different mechanisms for filtration, like interception, diffusion, impaction, and sieving, and maybe triboelectric that I want to stress these mechanism at the end of my speech. The nanofibrous structure, as they have a very large specific surface area, high porosity, facile functionalization method, small pore diameter, and maybe low mass in some cases, and high thermal stability, has a good candidate. Is a good candidate for application in several systems. For example, in industrial flue gas abandonment, indoor air cleaning, transportation, and filter masks, as we all of us used the filter mask during the corona pandemic. Okay, what is the main challenge and what is the problem of using nanofibrous material, and why should we functionalize them with the newly developed material like two of them that I want to speak about that. One of them is the porous materials like zeolites, activated carbons, and MOFs that I will introduce about MOF. Thanks to Batman to make it easy for me, because you know that what is MOF. The MOF briefly contains metal centers and metal nodes at the corner, and the organic ligands that will combine these metal nodes, and it will be grows in the three-dimensional and make it crystal. So these porous structures is very interesting because the main issue that they have is the larger specific surface area. The specific surface area is very high, and for example, in some cases, according to the surface area that obtained with BET analysis, is about 6,000 square meter per gram. They have a low density. You see that this structure is not have a volume, and there are many free space within this structure that could be very beneficial for us for the many applications like filtration, absorption, and gas storage. We can tune the size of these materials. We can easily functionalize them, not only after the synthesis, but also we can functionalize them during the synthesis and in situ growth of the metal-organic framework by functionalization of the ligands. Also, as I said, we use the many ligands. In the next slide, we can choose many ligands with different structure and different chain lengths, and we can coordinate these ligands with the metal corner and produce metal-organic framework with different structures. So, depending on the particulate matter size and what is our aim to filtrate or remove these particles, we can tune and rationally design our metal-organic frameworks, and depending to the particulate matter size. About the specific surface area, this figure shows you if you have a 1 gram of metal-organic framework and split it over the surface, you can completely cover the cycle field. This is about 10,000 square meter per gram. Not for all of MOF, but in some cases, the scientists have reported these MOF with some features like that. Okay, in this slide you can see many other MOFs with different structural morphology and pore size. And the yellow square shows the capacity for storage and the capacity for absorption of gas or particle. This is the free space that we can use it for many other applications, for example, the surface modification of fiber and textile or any other one. Okay, the application, because the time is concerning. Another interesting material is mixing. What is mixing? Mixing actually is a newly developed material synthesized from the metal carbide, and it's produced from the etching of max phase. And after the etching, you can see here that there are layered structure and this free space is very suitable for many applications. As in the next slide, I want to say about the functionalization and the seeds for the growth of metal organic frameworks. However, although MOF have several advantages, but this structure, for example, have a high surface area, high porosity, tailorability, but this structure may have a poor stability or low conductivity. The main problem, I think, is the low conductivity. On the other hand, we have a MXene structures, high volumetric capacitance, electronic conductivity, hydrophilicity, but on the other hand, self-restacking and oxidative degradation is the problem. How we can do, our suggestion is about the fabrication of MXene MOF composites mix of that the synergistic effect of MXene and MOF could overcome this limitation of both the component of this structure. You can see here the elements that are highlighted in violet and blue. The candidate elements for rational design of MOFs and MXene, and you can see that we have many cases that could be developed for the fabrication of MXene and MOF structure. This is only for the metal or the elements, not for the ligand. You can also use the many different ligands and tailor the structure by choosing the best ligand according to your application. Okay, in this schematic representation, you can see that after the etching of max space, we can access to the MXene structure. In situ synthesis of MOF, within the surface of the MXene could provide us the MXOF structure. For example, here I use ZIF8, zeolitic imidazole framework. 8 is based, this structure is based on the zinc. Very useful metal organic framework for applications in the biomaterial, because this structure is pH sensitive, and for example, for drug delivery application at acidic pH, this structure will be decomposed and the drug will be released. Here you can see the FESEM images of the MXene MOF. This MOF is ZIF8, and the MXOF structure, and possibly the MOF with the particle size about 50 nanometer are grown over the surface and within the structure of the MXene. Okay, we use this structure not only MXene, but also we use graphene oxide and composite metal organic framework with graphene oxide. And here you can see that the nanofiber, polyacrylonitrile nanofiber, pristine. Here is a nanofiber with graphene oxide, and in this SEM image, you can see the integration of metal organic framework reduced graphene oxide within the structure of nanofibers for several applications, but in this case, we studied it for particular matter removal. In the next slide, the PAN nanofiber, PAN ZIF 1% and 3%, you can see the structure of the cubic structure of ZIF8 within the nanofibers. And here is the SEM images of PAN and PAN MXOF in different weight concentration of MXOF structure. Okay, the mechanical properties of nanofibers is very obvious here, that we can use them, and they have actually appropriate mechanical properties. And in the case of particular matter removal efficiency here, in this 3 section, you can see the particle number concentration before and after filtration in the case of PAN, in the case of PAN metal organic framework and PAN metal organic framework reduced graphene oxide composite. And here you can see the transparency of the nanofibrous structure that provided, and you can see the Yaz University logo is completely crystal clear, and we can see this logo clearly. The interesting issue here is that the main that the fine particle has a more concentration in the particulate matter. We use the source of sense and the particles with different particle size generated and used for the particulate matter removal. It is interesting that to know that what is the effect of the thickness. Although we can estimate that more layer provide us more filtration efficiency, but however it is the contradictory that increasing the thickness we increase the pressure drop, and we should trade off between the pressure drop and the filtration efficiency. This is the reason why we investigate the effect of thickness of the nanofibers. And the most important thing is, I think, the relative humidity, because the nanofibers are used for the face masks, and the humidity for inhalation and exhalation may change the performance of our nanofibers. And here you can see that for different particle size, at the 10 to 55% of relative humidity, as the relative humidity increased, the filtration efficiency also decreased somehow, but is acceptable, and it completely affects the results of the, let me show it, and after that I will come back for the breeze monitoring. In this study, we try to use nanofibers not only for particulate matter removal, but also for, if it is possible, for breeze monitoring. And here, for example, you see the photograph of nanofiber that embedded within the two different types of masks. And this is a wire for measuring the resistance, and this is why we use the conductive component like mexine and reduced graphene oxide. Because the conductivity of nanofibers and effect of relative humidity on the conductivity will change the resistance and will provide us the real-time monitoring of breathing. Four types of the breathing is represented here: fast, normal, deep, and hold. You can see the amplitude of resistance in the normal and deep state is more than the type of fast or hold, and we are going to use this structure for breath monitoring and finding if a person cover mask, is it possible to predict the human health or not? This is the future of work. And we're going to go back to a slide that represents the effect of mexine and mexof. Here we use different concentration of mexine with polyacrylamide nanofiber with ZIF, and polyacrylamide nanofiber with different concentration and weight concentration of mexof. You can see that, for example, the 3% of PAN mexof provide us the better filtration efficiency. The same result was obtained about the drop pressure and actually the term of quality factor. The quality factor has both term of pressure drop and filtration efficiency, and the quality factor of this specimen was more than the others. The effect of the relative humidity and thickness are also represented. Okay, as a conclusion, to have the time, functionalization of nanofibers material with some porous and some conductive elements like mexine and, for example, metal could provide us higher specific surface area, higher air permeability, because this structure has porous characteristics. Low pressure drop could be obtained, electrical conductivity can be achieved because, and this is very important for us. For example, we should ZIF8 based on the zinc, because the zinc has a piezoelectric response. In another study, we studied the effect of adding mexine and mix-up based on the zinc to the PVDF nanofiber, the piezoelectric polymer, and we see the very good output voltage when we apply the mechanical force. And combining these ideas into one nanofibrous filter could provide us not only particulate matter removal, not only breath monitoring, but also to provide and generate the electricity, and we can use this structure for our further application with the electricity. Breath monitoring, appropriate mechanical properties, and high filtration performance. Let me to thank some of the agencies that provide us the funding, Sarmadan Elmi Federation, Iran Nanotechnology Initiative Council, and National Health Foundation, and also Yale University. Thanks to all my colleagues and the students. If you have a question, it will be appreciated. Thank you.
Thank you so much. Today it was very good. Time for questions. Any question, please? Please.
Thanks, Mendy. It was a very nice presentation. I have a question, maybe for upscaling. When you go to filter like non-wovens, like for filtration, most probably like microfibers with melt blown, or either ice lands in the sea melt spinning, and then like this hydro entanglement of them. What do you think like the application of these materials in developing better filtration products in larger scale, and what is the cost perspective? Because I think these are very expensive materials.
Actually, thank you for your question. Actually, we didn't study these materials for application in regular fibers, microfiber, or any other. We studied it only for nanofibers. About the upscaling of nanofiber, I think it's not a problem because we have several industrial electrospinning setup that could provide us the nanofibers filter with mass production. But in the case of the spunbond or any other regular non-movements, I think it is possible, maybe through the coating or end functionalization, surface functionalization, not during the fiber production. And the second question about the cost, unfortunately, this material has a high cost, and as we would like to study the effect of the newly developed material like mexines, the first report was on 2011 by the Yuri from the Drexel University. This is very new topic and very new material, but unfortunately the price is high, and maybe it's not cost benefit for the industry to develop this mass flows. But if I think we could provide and we could encourage them through the multifunctionalization of filter mass, not only for filtration, but also for heat monitoring, but also for example, the electricity generation or any other. Maybe in the first stage it could be luxury, but it will be promoted to the industry, I think, in the next years. Thank you.
Thank you so much. Unfortunately, there is no time for further questions, and I have to move on next.
Stage was that. Maybe paradox.
Okay, so let's go to the last presentation of today, exploring the combined effects of wavy geometric designs and material stiffness on artificial blood vessel biomechanics, presented by Galip Yilmaz. So please, is Galip here? Our last presenter. So he's not present, so we have to finish our session. In this session, we have learned about about radioactive waste and how to is it here? No. We learned about how to treat radioactive waste. After that, how to extract water from air as a new source. And the beauty about that is that you can have access to water everywhere, every time. So it is a kind of ambient intelligence for when you are thinking about it. And at the end of that, we have learned that we can use MOFs with nanostructures to produce some new and novel applications for the filtration technology. Thank you so much for attending this session, and please put your hand together for yourself. Thanks.
Sen oradayken deneyeyim ben. Olur mu?
Sayın Rektörüm, Sayın Protokol, kıymetli hocalarım, değerli katılımcılar. Sempozyumun kapanış oturumu ve ödül törenini gerçekleştirmek üzere son oturumu başlatıyoruz. Sempozyumun kapanış konuşmasını yapmak üzere üniversitemizin rektörü Profesör Doktor Mustafa Berktaş hocamızı kürsüye arz ederim.
Sayın Rektörüm, değerli hocalarım, sevgili katılımcılar. Sona doğru hep sabırsızlık oldu. Çok vakti iyi kullanmak lazım. Ben sizi misafir etmekten dolayı duyduğum memnuniyeti bir kez daha sizinle paylaşmak istiyorum. Bu özellikle uluslararası alana taşınmış bu sempozyumda bizim de topik alanımız olan biyomedikal mühendislik ve malzeme ile ilgili konuların konuşulması da ayrıca bizim açımızdan sevindirici bir yön oldu. Ben bu güzelliklerin artarak devam etmesi ve hocamıza da, değerli Yusuf hocamıza da bundan sonrasında da hem kurumsal hem kişisel olarak daha fazla katkı vermeyi söz vererek burada yararlı bir kongre geçirdiğimizi umarak hepinize katkılarınız ve katılımlarınız için teşekkür ediyorum. Sağ olun, var olun.
Sayın hocamıza konuşmaları için teşekkür ederiz. Kapanış konuşması yapmak üzere Profesör Doktor Ali Demir hocamızı kürsüye arz ederim.
Sayın Rektörüm, değerli arkadaşlar, İzmir Bakırçay Üniversitesi'nde 2 güzel gün geçirdik. ULPAS tarihinde çok önemli bir sempozyum oldu. Ben öncelikle Rektör Hocama çok teşekkür ediyorum. Bize hem ev sahipliği yaptı hem bütün imkanlarını verdi. Bu uluslararası sempozyuma büyük bir destek oldu. Kendisine cidden çok teşekkür ediyorum. Ayrıca dün gala yemeğinde de konuştuğumuz gibi lokalden, yani İzmir Bakırçay Üniversitesi'nden bize destek olan Cem Gök hocama ve tüm ekibine ayrı ayrı teşekkür ediyorum. Bu sempozyumlar, evet 15.sini organize ediyoruz ama bu destek olmaksızın bunun gerçekleşmesi mümkün değildi. Ama büyük bir keyifle, büyük bir heyecanla bu desteği bize verdiler. Bu sayede de bu sempozyum gerçekleşti. Dün sabah başladık. Açılış oturumu sonrasında, açılış oturumunda 2 davetli konuşmacımız vardı. Uluslararası boyutta 2 davetli konuşmacımız vardı. Arkasından öğle arası ve ondan sonraki oturumlarda toplam 40 bildiri sunuldu. 30 da poster sunuldu. ULPAS tarihinde bu kadar posteri biz ilk defa görüyoruz. Özellikle Ar-Ge merkezlerimizden ciddi katılım oldu. Bu katılıma da gerçekten teşekkür ediyoruz. Sempozyum bildirileri hem içerik olarak iyiydi hem de tartışmalar olarak iyiydi. 2 paralel oturumda yaptığımız için çok büyük salonlar olmasına rağmen yeterli katılım söz konusuydu ve büyük bir ilgiyle her oturumda sorularla, tartışmalarla bildiriler tartışıldı. Hedef zaten buydu. Yani çalıştığımız laboratuvarlarda çalıştığımız bilgilerin gün yüzüne çıkması, ortak paylaşılması ve bu sayede de yeni ortaklıkların, yeni arkadaşlıkların, yeni dostlukların, yeni proje girişimlerinin başlatılmasıydı. Bunun olduğuna ben inanıyorum. Bunun somut örneklerini görmek gerçekten bizi çok sevindiriyor. Dolayısıyla biz 15. ULPAS'ı İzmir Bakırçay Üniversitesi'nde yapmaktan çok büyük keyif aldık, çok büyük mutluluk duyduk. Ben tekrar rektörüme ve tüm arkadaşlarıma çok teşekkür ediyorum. Bir sonraki sempozyumun henüz daha yerini ve zamanını kesinleştiremedik ama en kısa zamanda bunu anons edeceğiz. En kısa zamanda da sempozyumdaki sunulan bildirilerin yer aldığı ve davetli konuşmacıların sunumlarının yer aldığı bildiri kitapçığına hukuk prosedimizi yayınlayacağız. Böylece 15. ULPAS'ın dönüşü tamamlanmış olacak. Bundan sonra da 16. ULPAS'ın hazırlıklarına başlayacağız. I just want to say a few words to our international friends. I really appreciate and thank for their efforts and being here with us and sharing their experiences. And with this collaboration, ULPAS has become an international event, and we would like to see more of you and your friends in the symposium. And perhaps one day we are also hoping, planning, or dreaming to host or hold this symposium in an international place. Could be in Egypt, could be in Qatar, or could be in England or somewhere else. And we do hope this to organize one day, and I'm sure that will happen one day. Once again, before closing, I welcome you all, I thank you all, and hope to see you again in the future symposium. Thank you very much.
Sayın hocamıza konuşmaları için teşekkür ederiz. Sempozyumun ödül törenine geçiyoruz. Sözlü bildiriler kategorisinde birinci seçilen bildiri ödülünü almak üzere Profesör Doktor Sabit Adanur hocamızı sahneye davet ediyoruz. Hocamıza ödülünü vermek üzere rektörümüz Sayın Profesör Doktor Mustafa Berktaş hocamızı kürsüye davet ediyoruz. Sözlü bildiriler kategorisinde ikinci seçilen bildiri ödülünü almak üzere Doktor Bahman Bostani'yi sahneye davet ediyorum. Hocamıza ödülünü vermek üzere Profesör Doktor Ali Demir hocamızı sahneye davet ediyorum. Sözlü bildiriler kategorisinde üçüncü seçilen bildiri ödülünü almak üzere Almutasim Salame hocamızı sahneye davet ediyorum. Hocamıza ödülünü vermek üzere Profesör Doktor Cem Gök hocamızı sahneye davet ediyorum. seçilen bildiri ödülünü almak üzere İkbal Gözde Topçanoğlu hocamızı sahneye davet ediyorum. Hocamıza ödülünü vermek üzere Profesör Doktor Yusuf Ulcay hocamızı sahneye davet ediyorum. Poster bildiriler kategorisinde ikinci seçilen bildiri ödülünü almak üzere Doktor Oydum Çalpankan Güneş hocamızı sahneye davet ediyorum. Olur hocam. Hocamıza ödülünü vermek üzere Doçent Doktor Seyit Mansur Bidokye hocamızı sahneye davet ediyorum. Sözlü bildiriler kategorisinde üçüncü seçilen bildiri ödülünü almak üzere Doçent Doktor Uğur Özveren hocamızı sahneye davet ediyorum. Hocalarımıza ödülünü vermek üzere Profesör Doktor Özgür Kübül Özmen hocamızı sahneye davet ediyorum. Ödül töreni sempozyum sponsorlarına verilecek ödüllerle devam edilecektir. Sempozyuma olan katkılarından dolayı hediye verilmek üzere Innovenso temsilcisini sahneye davet ediyorum. Ödülü vermek üzere Profesör Doktor Ali Demir hocamızı sahneye davet ediyorum. Sempozyuma sponsor olan RB Kalesi temsilcisini hediyelerini almak üzere sahneye davet ediyorum. Hediyeyi vermek üzere Doçent Doktor Haşim Özgür Tabakoğlu hocamızı sahneye davet edelim. Amerika temsilcisini hediyelerini almak üzere sahneye davet ediyorum. Hediyelerini vermek üzere doçent doktor Ümit Hüseyin Kayar hocamızı sahneye davet ediyorum. Sempozyuma sponsor olan Kadife Tex temsilcisini hediyelerini almak üzere sahneye davet ediyorum. Hediyelerini vermek üzere doçent doktor Tarkan Akderya hocamızı sahneye davet ediyorum. Sıradan İzmir Bakırçay Üniversitesi Rektör Hocamız Profesör Doktor Mustafa Berktaş Hocamızın üniversite hatıramız olarak hediye takdimleri olacaktır. Hediye takdimi için hocamızı sahneye davet ediyorum. Hediyelerini almak üzere Profesör Doktor Ali Demir hocamızı sahneye davet ederim.
Değerli katılımcılar, biraz renk gelsin istedik. Bizim üniversitemizin yakınlarında kuş cennetimiz var. Kuş cennetinin ana üyeleri de flamingolar. Biz bu nedenle üniversitemizin maskotunu flamingo olarak belirledik ve ismini de Bakır koyduk. İlk defa bugüne yetiştirme şerefine eriştik ve biz buradaki değerli katkıda bulunan organizasyonun başındaki değerli hocalarımıza izninizle bunları vermek ve sizleri de Bakır'la tanıştırmak istiyoruz.
Profesör Doktor Yusuf Ulcay hocamızı sahneye davet ediyorum.
Naci Hocam aramızda yok. İzninizle onun hediyesini de hocama iletmek üzere takdim ediyorum.
Hocalarımıza teşekkür ederiz. Değerli katılımcılar, ödül törenimiz burada sona ermiştir.
Arkadaşlar, herkes sahneye
Onu da ayrı fotoğrafı çekelim.
Oturumumuz kapanış değerlendirme toplantısıyla devam edecektir.
Değerli arkadaşlar, bir 15 dakikanızı rica edeceğim. Hep biz konuştuk, hep bir şeyler söyledik, hep organizasyon yaptık. Sizi dinlemek istiyoruz biraz daha. Dolayısıyla yani sizin görüşleriniz, eleştirileriniz, tavsiyeleriniz çok önemli bizim için. Bir 15 dakika kadar bir değerlendirme istiyorum. Söz almak isteyen arkadaşım varsa memnuniyetle buyursun. Yoksa ben arkadaşlardan rica edeceğim görüşlerini isteyeceğim. Söz almak isteyen arkadaşımız var mı? Değerlendirme adına 15. unutmasın. Hocam buyurun. Mikrofon verebilir miyiz? Can hocam. Yani bir mikrofon var mı bunlardan? Peki, dinliyoruz. Mikrofona geliyor zaten.
Hocalarım, kıymetli hocalarım, öncelikle bu kongre için herkese çok teşekkür ederim. Ben Sivas Cumhuriyet Üniversitesi'nden doçent doktor Ebru Yabaş. Bu kongreye firma aracılığıyla, benim firma danışmanlıklarım var. Firmamın yönlendirmesiyle ben bu kongreyi fark ettim ve onlarla olan bir çalışmamızı sunmak için katıldım. Öncelikle çok teşekkür ediyorum. Gerçekten üniversite sanayi işbirliği anlamında dün görüşmüş olduğum firmalar da oldu. Yine İzmir Bakırçay Üniversitesi ile de ortak yapabileceğimiz çalışmalar da oldu. Bu bağlamda ben çok teşekkür ediyorum. Bizim için çok güzel de bir etkinlik oldu bu açıdan. Ben aynı zamanda Sivas Cumhuriyet Üniversitesi İleri Teknoloji Uygulama Araştırma Merkezi Müdürüyüm. Burada sağ olsun Cem Hocam yönlendirmesiyle hem bölümlerdeki hem de araştırma merkezindeki olanakları görme imkanım oldu. Ben aslında İzmir Bakırçay Üniversitesi ile Sivas arasında da bu kongre vasıtasıyla bir ortak işbirliği protokolü de yapmak istiyorum. Hocamla zaten sık sık görüşeceğiz inşallah. Bu anlamda ben çok teşekkür etmek istiyorum. Gerçekten örnek olabilecek bir kongre, özellikle sanayi, ARGE merkezlerini buluşturan, biz üniversiteyle buluşturan bir kongre olması açısından bu tür kongrelerin bence sayısının artması gerekiyor. Benim ilk böyle sanayi işbirlikli bir kongre katılımım. Bu anlamda da çok teşekkür ediyorum hocam. Bunları ben dile getirmek istedim. Size ayrıca zaten dile getirecektim sayın rektörlerimize, hocalarımıza. Buradan da söylemiş olayım. Çok teşekkür ederim. Emeklerinize sağlık.
Bu demektir ki ULPAS hedefine ulaştı.
Hocam, Sivas Cumhuriyet Üniversitesi adına amacına çok güzel ulaştı. İnşallah devam edecek çalışmalar. Hem firmalarda hem üniversiteyle inşallah hocam. Teşekkür ederim.
Başka söz almak isteyen var mı? Yoksa ben Sabit Hocam'a söz verecektim. Sabit Hocam zaten el kaldırdı. Hocam buyurun. Çünkü Sabit Adam Hocam Amerika'dan geldi. Türkiye'de şu anda postdoc, özür dilerim, sabatik olarak bulunuyor ama bütün deneyimi, bütün akademik hayatı Auburn Üniversitesi'nden bu tür faaliyetlere değerlendirebilecek inanılmaz bir birikimi vardır. Buyurun hocam.
Teşekkür ederim Ali. Davet ettiğiniz için çok teşekkür ederim. Her şeyden önce çok güzel bir kampüsünüz var. Çok sevdik, çok beğendim kampüsü. Tam bir adeta tatil yeri. Yani tropik bir yerde tatil yeri gibi palmiye ağaçları falan. Çok güzel. Binalar da çok güzel dizayn edilmiş. İşleri de çok güzel, rahat, konforlu. Teknik yöne gelince çok yüksek kaliteli sunumlar oldu. O yüzden herkese çok teşekkür ediyorum. Ben tahmin ettiğimden, umduğumdan çok daha yüksek kaliteli sunumlar vardı. Hani state of the art teknoloji dedikleri teknolojinin son merhalelerini arkadaşlar anlattılar. O yüzden ayrıca memnun oldum. İnşallah tekrar devam eder bu tip şeyler. Biz de katılmaya çalışırız.
Çok teşekkür ederim hocam. Sağ olun.
İyi günler.
Başka söz almak isteyen? Cem Hocam buyurun.
Hocam teşekkür ederim. Sanırım sözü almak isteyen yoktu diye düşünerek son sözü almak istedim.
Son söz değil hocam, ben söz vereceğim.
Hocam,
yani,
buradaki son söz hocam. Son söz sizde.
Arkadaşlar söz almak istemiyorlar, mikrofonu bence konuşuyorlar. Onu biliyorum, o yüzden ben söz vereceğim.
Ben unutmadan Sayın Rektörüme çok teşekkür etmek istiyorum. Bu organizasyonun her aşamasında bize destek oldu. Sadece sözde değil, her zaman yanımızda olduğu, ihtiyaçlarımızı sorduğu, bize her türlü imkanı sunma konusunda hep yanımızda oldu. Hocamıza minnettarlığımı sunarak özellikle rektör hocamız için kuvvetli bir alkış istiyorum. Sonrasında Sayın Ali Hocam ve Yusuf Hocam bize öncülük ederek bu organizasyonun var olmasında çok çalıştınız. Sizden de çok şey öğrendik. Sizlere de çok teşekkür ederek hocalarımıza da bir alkış istiyorum. Lütfen çok teşekkürler. Bir de ekibimiz var. Hem İTÜ'den, Bursa Teknik'ten, Uludağ Üniversitesi'nden ve Bakırçay Üniversitesi'nde adına tek tek sayamadığım arkadaşlarım burada çok koşturdular ve genç arkadaşlarımız da var. Terlediler, yoruldular ama bence de çok güzel bir tecrübe de kazandılar. Onlar için de bir alkış hak ettiklerini düşünüyorum. Ve sayın katılımcılar, bizleri onurlandırarak saygıdeğer katılımlarınız için en içten teşekkürlerimi sunmak istiyorum. Bu sempozyum sizlerle birlikte oldu ve üniversitemizde de onurlandırdınız. İnşallah sizleri tekrar burada görmek istiyoruz.
Çok teşekkürler. Evet, şimdi Muhammed Rıza'nın görüşlerini dinlemek istiyorum ben. Hollanda'dan kalkıp geldi. Türkçe'de konuşuyor. Dolayısıyla but you can also speak in English if you want. However you feel.
Merhaba, size ve herkese burada. Teşekkür ederim. Çok iyi kaliteli bir sempozyum. Yani Senay'dan da duydum. Çok burayı tanıyorlar. Bu sempozyum ULPAS sadece akademik değil, akademikle endüstrinin ortasında hep bunları buluşturmak istiyor. İnşallah yani sadece as a suggestion daha söylediniz yani kendiniz daha bunu genişletmek ve uluslararası yapmak yani %50 burada başka ülkelerden olsun diye inşallah olabilir ve çok teşekkür ederim. Çok sevindim ve inşallah beraber de çalışacağız. Bazı burada kontaklar oldu. Onun için teşekkürler.
Evet, bu sempozyumlarda bize büyük destekler veren Yasemin Tatar hocam var. Yalova Üniversitesi'nden. Onun sesini hiç duymadık. Görüşlerini almak isteriz. Hocam.
Yasemin Tamer.
Yasemin Tamer, özür dilerim.
Teşekkür ediyorum hocam. Biz de 12. ULPAS'ta dahil olduk ULPAS'a. Bu 4. ULPAS'ımız. Yani çok teşekkür ediyoruz. Yalova Üniversitesi'ne de size destek olmaya çalıştık. Bakırçay Üniversitesi'ni çok sevdik. Hem Cem hocam, rektör hocam, arkadaşlar, bütün hoca arkadaşlarımız herkes çok destek oldular. Teşekkür ediyoruz. Yani ilk girdiğimizden bu yana tabii ki ULPAS her seferinde güncelleniyor. Yani biz de öğreniyoruz, bir şeyler öğreniyoruz. Kongreden de güncelleniyor. İşte ben teşekkür ediyorum hocam her şey için. Çok sağ olun. Söz verdiğiniz için de herkese de misafirperverlikleri için teşekkür ediyoruz. İnşallah ondan da görüşmek üzere.
Now I would like to hear the voice of Professor Doğanay. He's from Iran, American University, and I believe this is the first time you are coming to our ULPAS, and would like to hear your opinion about ULPAS.
Hello everyone, thank you Professor Demir, and I would like to thanks from the organizing committee, especially you, Dr. Bileki, Dr. Ojay, and Professor John in Bakırçay University and head of this university for this organization and this nice conference here. And I'm so happy to find the new friends here and find some new opportunities for future collaborations. Thank you. Thank you.
We thank you also. Şimdi sahiden bir arkadaşıma söz vermek istiyorum. RB Karesi bize hem sponsor oldu, altın sponsor oldu, hem de bizi gerçekten destekleyen bir firma. Kendilerine özellikle teşekkür ediyorum ama Ömer Bey'in de görüşlerini duymak isteriz. Buyurun.
Herkese merhaba, ben Ömer Atalay, RB Tekstil'deyim. 8 sene oldu RB Tekstil'de. Daha önce tarz organizasyona çok katılmıyorduk ama Doğan Bey'le beraber aslında daha çok tarz organizasyonu içerisinde bulunduk. Bunun çok faydalı olduğunu düşünüyorum. Sanayi açısından çok faydalı. Farklı alanlarda farklı getiriler, sunumlar gördüğünüz zaman aslında bunun sanayide uygulama açısından bizim için çok faydalı olduğunu düşünüyoruz. Doğan Bey şu an burada değil, orada olduğu için katılamadı. Selamlar var bize. Biz hocama, Ali hocama ve Profesör Doktor Rektörümüz Mustafa Aktaş hocamıza selamlar var. Biz herhangi bir aslında olumsuz görmüyoruz bu sempozyumlarda. Daha çok aslında katılımın artırılması veya sponsorun artırılması belki bu organizasyonu daha iyi yere getirebilir. Onu söyleyebilirim ancak. Onun dışında biz yani düzenli bir şey açısından bir tabii eksik görmüyoruz. Dediğim gibi ne kadar fazla şey olursa, katılım olursa o kadar fazla çeşitlenecek, o kadar fazla aslında ileri gidecek. Bunlar bu çalışmanın içinde Karaseks olarak çok teşekkür ederim herkese. Emeği geçen.
Biz teşekkür ediyoruz. Çok sağ olun. Ahmet Avcı hocamın koridorda bana ilettiği bir teklifi vardı. Bütün heyetin duyması bakımından Ahmet Avcı hocama mikrofonu verelim.
Öncelikle teşekkür ederim. Bu sempozyumlara devam ettiriyorsunuz. Sempozyuma başlarken Bursa'da Tekstilciler İhracatçı Derneği vasıtasıyla tekstil konularla ilgili yarışmalar var. Yarışmanın arkasından başladı ve 15.ye geldiniz. Bu bakımdan gerçekten tebrik ederiz. Güzel çalışmalar. Bu sempozyum her ne kadar uluslararası olarak yayılsa da hani Türkiye'den başka onu bilen, duyan çok az, çok nadir. Bunun Web of Science'a, skollara veya diğer şeylere girilerek oralara nasıl kaydoluyor veya nasıl oralara şeyleri bilemiyorum. Oralardan taranır hale gelirse daha iyi uluslararası olur. Daha başarılı olur zannediyorum. Çünkü biz o seviyeye geldiğimize inanıyorum. İkinci olarak bu bir kitap çıkarılabilir bu sempozyumlardan. Ayrıca TR dizinli veya önce TR dizinli başlar, sonra ilerleyebilir. Hatta SCI'ye girebilir bu çalışmalar. İki kollu da gidebilir. Teklif olarak bunu söylüyorum. Ama dediğim gibi bugün doçentlik başvurularında veya üniversitelerde üniversite girişlerinde birçok üniversite sempozyum ve kongreleri Web of Science'da taranıyor olmasını istiyorlar. Sempozyumların, kongrelerin. O vakıftan daha o tarafa doğru yönlenmesi teklifimizdi. Sizlerle konuşmuştuk. Artık değerlendirme sizlere ait. Teşekkür ederim.
Hocam biz teşekkür ederiz. Biz 3 yıldır yaptığımız sempozyumlardan sonra seçilmiş bildirilerin TR dizinde olan Journal of Innovative Engineering dergisinde yayınlanmasını teklif ediyoruz. Yayınlanan makalelerimiz var. Eğer burada sunum yapan arkadaşlar bildirilerini Journal of Innovative Engineering dergisinde değerlendirmek isterlerse oraya yönlendiriliyor, orada yayınlanıyor. İkinci olarak ULPAS doçentlik kriterlerini sağlayan bir sempozyum, uluslararası sempozyum. Orada bir sorun yok. Tek eksiğimiz akademik teşvikte eksiğimiz var. Ancak başlı başına uluslararası bir dergide yayınlanması tabii ki bizim de arzumuz ama SC'ye datalarından bir dergide yayınlanması bizim de arzumuz. Önümüzdeki günlerde bunun üzerine de çalışacağız. Hocam çok teşekkür ediyorum. Son olarak bir arkadaşıma daha söz vermek istiyorum. Nazire Hocam, Uşak Üniversitesi Tekstil Mühendisliği Bölüm Başkanı. Görüşlerimizi paylaşırsa çok memnun oluruz. Bu son olacak. Böylece tamamlamış olacağız.
Çok teşekkürler hocam söz hakkı verdiğiniz için. Burası daha önce hocamızın da belirttiği gibi işbirlikleri açısından çok verimli oldu benim için de. Aylardır bulamadığım bir firma ismini bulabildim ve ortak çalışma teklifleri de aldım. Çok güzel fikirler de elde ettim. Ar-Ge firmalarından bir katılımcının bir yorum olmuş hocam, ben onu size aktarmak isterim. İngilizce dilinde sunumlar yapılıyor ama katılımcıların çoğu Türk şeye daha hakim. Acaba çift dili gibi onlara senkronize Türkçe tercih yapılabilir mi? Yani o sistem çok mu pahalı olur, çok mu zor olur? Hani kolay olabilirse katılımcıların daha çok faydalanabilmesi için Türkçe'de düşünülebilir diye yorumlamak istedim.
Hocam çok teşekkür ediyoruz. Simultane tercüme oldukça maliyetli bir işlem. Yani arzu ediyoruz ama bizim bütçemizi aşan bir konu. Ümit ediyorum günün birinde o bütçeye ulaşırız ve onu da gerçekleştiririz. Buradaki yaklaşımımız şu oldu. Uluslararası bir bildiri, uluslararası bir sempozyum olması dolayısıyla tüm bildirilerin İngilizce sunulmasını istiyoruz. Ancak Ar-Ge merkezlerinden gelen arkadaşların bu imkan olmadığı için onlara da ayrı bir oturum halinde Türkçe sunumlar imkanı verdik. Bu sempozyumda bir hayli başarılı bir şekilde çalıştı. Evet, tekrar katılımınız için çok teşekkür ediyorum. Ben şimdi toplu fotoğraf, aile fotoğrafı için sizi buraya davet ediyorum.
Pazarlık milyon.
Arkadaşlar buyurun.
Orada oturanlardan para alıyor.
Biraz daha bilebilir misiniz? Arkalarına doğru. Arkalara doğru geçebilirsiniz biraz daha. Hocam sizi biraz daha öne alabiliriz.
Arkadaşlarımızın bir kısmı çökebilir.
Evet, uzun. Bizim de tuzağa arkaya doğru geçebilirler. Evet, bu şekilde alıyor. Gözüküyor hocam, sorun yok şu an. Hocam şu an sorun yok.
Şu anda sorun yok hocam.
Hocam bu şekilde iyi çekiyorum şu an. Evet, çekiyorum. Teşekkür ederim.
Değerli katılımcılar, sempozyuma katılımınız için teşekkür ederiz. fuaye alanında ikramlarımız bulunmaktadır.